There is a layer of rock buried deep beneath your feet that should not exist. It is thin, in most places no wider than your thumb, but it runs through sediment cores pulled from the bottom of the Atlantic, from Arctic permafrost, from the floors of ancient seas on 6 continents. The same chemical signature, the same anomaly, the same moment in time, pressed into the geology of the entire planet. In 2018, a climate scientist at the NASA Goddard Institute for Space Studies published a peer-reviewed paper asking a question no one in mainstream science had formally asked before. If an industrial civilization had existed on Earth millions of years before us, would we even be able to detect it? The answer was no. Not probably not. No. The geological record is incomplete. Tectonic processes recycle the ocean floor every 200 million years. Every coastline from 12,000 years ago is now submerged beneath 400 feet of water. And the chemical fingerprint of a civilization burning fossil fuels looks in the rock almost identical to a volcanic eruption. Nobody had looked. That is the part that stays with you. Tonight, we follow the evidence. A scar in 56-million-year-old rock, a cosmic catastrophe that may have ended a chapter of human history, and a temple built before agriculture existed by people who should not have been able to build it. We will trace the anomalies, examine the geology, and sit with the question that one NASA scientist put into print, and the rest of the scientific world has struggled to answer since. If this is the kind of journey you want to take, subscribe and leave a like. It makes an enormous difference. The rock is patient. It has been waiting a very long time, and we are only just learning how to read it. Start with what we know for certain. The Earth is 4.5 billion years old. Complex animals have existed on its surface for more than 500 million years. Mammals have been here for over 200 million. And in all of that time, across all of those eons, through every ice age and mass extinction and continental collision, our civilization, the one that builds cities and splits atoms and sends machines to other planets, has existed for roughly 300 years. 300 years out of 4.5 billion. If you compress the entire history of this planet into a single 24-hour day, our industrial civilization would appear in the final fraction of the final second before midnight. Not the final second, a fraction of it. Everything we have ever built, every road and tower and power grid and satellite, would occupy a sliver of time so thin you could not see it without a microscope. Now hold that thought. Hold it carefully, because it is about to change the way you think about everything that follows. In 2018, 2 scientists sat down and asked a question that sounds simple, but turns out to be one of the most unsettling questions in the history of science. The question was this: if an industrial civilization had existed on Earth millions of years before us, would we be able to find it? Not, did one exist? That is a different question entirely. The question they were asking was subtler and in some ways more disturbing. It was a question about the limits of what we can know, about the reliability of our own tools, about whether the story we tell ourselves, that we are the first, that nothing like us has ever existed on this planet before, is a conclusion supported by evidence, or simply the best guess available given how little of the record we can actually read. The 2 scientists were Adam Frank, an astrophysicist who had spent his career thinking about the conditions for life and intelligence across the universe, and Gavin Schmidt, a climate scientist who at the time was serving as the director of the NASA Goddard Institute for Space Studies in New York. These were not fringe thinkers. These were not researchers operating at the edge of credibility. Frank had hundreds of peer-reviewed publications. Schmidt was one of the most respected climate modelers in the world, running one of the most important climate research institutions on the planet, and doing so under the auspices of NASA. They published their paper in the International Journal of Astrobiology. They called it the Silurian Hypothesis, a name borrowed, with a deliberate wink, from a 1970 episode of the British science fiction series Doctor Who, in which a race of intelligent reptilian creatures called the Silurians is discovered to have inhabited the Earth hundreds of millions of years before humans. Frank and Schmidt were not claiming that lizard people built cities in the Jurassic. They were asking something precise and carefully bounded. Would the geological record preserve a detectable signal of an industrial civilization that had existed and collapsed millions of years in the past? And the answer they arrived at, after a thorough and honest examination of what the geological record can and cannot tell us, was probably not. That answer deserves a moment. It does not mean a previous civilization existed. Frank and Schmidt were explicit about that. They stated clearly that they considered the existence of a prior industrial civilization to be extraordinarily unlikely. What they were doing was not building a case for lost history. They were probing the architecture of a knowledge claim, the claim that we are the first. And what they found was that this claim rests not on positive evidence that nothing came before, but on the absence of evidence, and that the absence of evidence, in a system where evidence is systematically destroyed over time, is a very different thing from proof. Here is the key concept. It is worth understanding properly because everything that follows depends on it. When scientists talk about what we can detect in the geological record, they are talking about what survives. And what survives across millions of years is a tiny, unrepresentative fragment of what once existed. The geological record is not a complete archive. It is more like a library where most of the books have been burned. Many of the surviving pages are water damaged, and large sections of the shelves are simply missing. What remains is real. It is genuine evidence of real events, but it is incomplete in ways that are easy to underestimate. Frank and Schmidt focused their analysis on what an industrial civilization would actually leave behind. Not monuments, not cities, not artifacts. Those are the things we instinctively imagine when we think about the traces of a civilization. And those are precisely the things that do not survive on geological timescales. What survives, if anything survives at all, is chemistry, isotopic signatures, elemental anomalies, the faint, indirect fingerprints of processes that altered the composition of the rock or the atmosphere in ways that persist long after everything structural has been destroyed. And when they asked what kind of chemical fingerprint an industrial civilization would leave, what they found was this. It would look very much like certain natural geological events that we already know occurred. Events that we already have explanations for. Events whose causes we think we understand. That is the problem. That is the heart of it. The Silurian hypothesis is not a theory about the past. It is a theory about the present limits of our knowledge and our tools. It is a formal scientific acknowledgement that we cannot rule something out. And in science, knowing what you cannot rule out is just as important as knowing what you can. There is a thought experiment worth sitting with before we go further. Imagine that our civilization ends tomorrow. Not in a catastrophe, not in a war, just a quiet exit. The machines stop. The lights go out. Humanity is gone. What happens next? Within weeks, most power grids fail. Within months, vegetation begins reclaiming the cities. Roots crack the pavement. Vines pull at the walls. Within a few decades, wooden structures collapse. Steel corrodes. Glass fractures under thermal stress. The buildings we think of as permanent begin their long return to rubble. Within a few centuries, most above-ground structures are gone. Within a few thousand years, the rubble is buried under soil and sediment. The locations of our greatest cities are unmarked mounds in a landscape that has moved on. Within 100,000 years, the only detectable traces of our existence are geological, thin bands of unusual chemistry in the rock, elevated heavy metals from our industrial processes, synthetic polymer fragments that do not occur in nature, radioactive isotopes scattered globally by our nuclear weapons tests, a sharp anomaly in the ratio of carbon isotopes in sedimentary layers, recording the moment we began burning vast quantities of ancient organic carbon and releasing it into the atmosphere. Within 1 million years, tectonic processes have resurfaced entire regions. Rivers have changed course. Mountain ranges have shifted. The specific locations of our cities are no longer identifiable from the surface, and much of the chemical signal has been diluted, compressed, or overprinted by other geological events. Within 10 million years, the ocean floor on which some of our greatest ports once stood has been dragged into subduction zones, pulled down into the mantle at the boundaries of tectonic plates, where temperatures and pressures melt everything back into magma. Our cities, our roads, our monuments, dissolved. The atoms that made up our skyscrapers are now cycling through the interior of the Earth, indistinguishable from the atoms of everything else. Within 50 million years, virtually nothing physical remains. The chemical signatures persist in places, anomalous layers in deep sediment cores, subtle isotopic shifts in the rock record. But they are thin, ambiguous, and easily misread. A geologist 50 million years from now, pulling a core sample from what was once the coast of North America, might find a strange layer, an unusual concentration of certain elements, a carbon isotope excursion. They would run tests, they would build hypotheses, and in almost every case, the hypothesis they would reach for first would not be a previous civilization. It would be volcanism, a methane release, an orbital shift, something natural. Because those are the tools science has. Those are the categories that exist. And the signal left by an industrial civilization fits inside those categories almost perfectly. Think about that. A civilization that built everything we have built, that altered the atmosphere and the oceans, that left its chemistry stamped into the geology of the entire planet. And 50 million years later, the evidence is a thin line in the rock that looks like a volcano. Now take that thought and run it in reverse. We are the ones with the core samples. We are the ones pulling sediment from ancient seafloors and reading the chemistry of vanished eons. And in those records, we have found events, real, documented, anomalous events, that do not fit neatly into our existing explanations. Events where enormous amounts of carbon entered the atmosphere in a geologically brief period. Events where global temperatures spiked dramatically. Events whose triggers, despite decades of dedicated research, remain partially or entirely debated. We have explanations for these events. Reasonable, evidence-based explanations. But the explanations are not complete. The evidence is not fully resolved. And Frankenschmidt's contribution was to point out, with precision and care, that if one of these events had been caused by a previous industrial civilization, we might not be able to tell. The absence of a civilization in the geological record is not the same as evidence that no civilization existed. It is important to feel the weight of that distinction, not to misuse it. The claim is not that a civilization did exist, and we will not make that claim here. The claim is that we cannot rule it out with the confidence we have assumed. And that is a genuinely different epistemic position than the one most of us have been standing in. Now here is the question that makes this more than an abstract philosophical puzzle. The Earth is 4.5 billion years old. Complex life has existed here for more than 500 million years. Mammals have been here for over 200 million. Dinosaurs alone dominated the planet for 165 million years. Longer than the time that has passed since they disappeared. Longer than any of us have an intuition for. And some of those dinosaurs had relatively large brains. Some lived in complex social groups. Some showed behavioral sophistication that continues to surprise researchers who study them. We arrived 300,000 years ago. We went from stone tools to a global technological civilization in about 12,000 of those years. We have been industrial for 300. The question Frank and Schmidt were really asking, beneath the geology and the isotope chemistry, is whether we have been humble enough about deep time, whether we have genuinely reckoned with how much could have happened in 500 million years, whether our confidence in our own uniqueness is earned, or whether it is, in some sense, the default assumption of creatures who can only see a tiny fraction of the record and have filled the gaps with the most convenient story available. The answer to that question begins in the rock, in a specific layer of sediment pressed between ordinary geology at a depth corresponding to roughly 56 million years ago, where something happened to this planet that the science has still not fully explained. Here is what the Earth is, at its most fundamental level, as a geological system. It is a machine that destroys its own history. Not carelessly, not occasionally, systematically, continuously, and with a thoroughness that is almost difficult to comprehend. The surface of this planet is not a stable archive. It is an active, churning, recycling process that has been running for 4.5 billion years, and it does not preserve the past. It consumes it. Start with the ocean floor. The seafloor is generated at mid-ocean ridges, the vast underwater mountain ranges that run through every ocean basin on Earth, where tectonic plates pull apart and magma rises from the mantle to fill the gap, cooling into new oceanic crust. This crust spreads outward from the ridges, moving slowly across the ocean floor until it reaches a subduction zone, a place where one tectonic plate dives beneath another and is dragged back down into the mantle, where it melts. The oldest oceanic crust on Earth is approximately 200 million years old. Everything older has been destroyed. Every piece of seafloor that existed before that, every sediment layer, every chemical record, every fossil, every trace of anything that happened on or near the ocean floor in the first 4 billion years of Earth's history, has been melted back into the interior of the planet. Gone, not hidden, gone. And this matters enormously for the question we are asking, because the ocean covers 71% of the Earth's surface. If anything lived or built or left a record near the ocean, on coastlines, on continental shelves, in shallow seas, and if that record is more than 200 million years old, it no longer exists. The ocean swallowed it, and the mantle dissolved it. Continental crust is older. Some rocks on the continents are nearly 4 billion years old. But the exposed continental surface from before the last 2.5 million years, the Quaternary period, is rare and fragmented. Most of the Earth's continental surface has been buried, eroded, metamorphosed, or deformed beyond easy recognition by the same geological processes that are still operating today. Finding undisturbed surface material from even 10 million years ago is a needle in a haystack problem. Finding it from 50 million years ago is exceptional. From 100 million years, rare to the point of improbability. And then there is erosion. Rain, wind, ice, rivers. The surface agents of destruction that operate on timescales far shorter than tectonics, but are no less thorough in aggregate. Mountain ranges that once stood higher than the Himalayas have been reduced to rolling plains. Coastlines have advanced and retreated by hundreds of miles. River deltas have built and rebuilt and been swept away. The landscape you are living in right now has been radically reorganized multiple times since even the most recent geological epoch began, and it will be reorganized again, long before anything we leave behind has a meaningful chance of surviving. Now add sea level. This is the factor that gets the least attention, and it may be the most important of all for understanding why the deep record is missing what we might expect it to contain. During ice ages, water is locked up in continental ice sheets, the vast glaciers that have periodically covered large portions of North America, Europe, and Antarctica. When those ice sheets grow, sea levels fall. During the last glacial maximum, approximately 20,000 years ago, sea levels were roughly 120 meters lower than they are today. That is nearly 400 feet. The coastlines of every continent extended far beyond their current positions. Vast areas of what is now open ocean were dry land, inhabited, habitable, capable of supporting large populations. The Sunda Shelf, the continental shelf connecting mainland Southeast Asia to the islands of Indonesia, Borneo, and the Philippines, was exposed as a continuous landmass roughly the size of India. The Sahul Shelf, connecting Australia to New Guinea, was dry. The North Sea basin between Britain and continental Europe was a landscape of rivers, forests, and grasslands. The Persian Gulf was entirely dry land, one of the most fertile and sheltered environments on Earth. The Indian continental shelf extended hundreds of miles further into the ocean than it does today. All of this terrain is now underwater, not gradually submerged over millions of years, but flooded, in geological terms quite rapidly, as the ice sheets melted at the end of the last ice age and sea levels rose by that 120 meters over roughly 10,000 years. The coastlines retreated, the lowlands flooded, the inhabited landscapes of the Ice Age world were drowned beneath the sea. And here is the thing that should stop you. Civilizations do not build in the mountains. They build on coasts. They build on river deltas. They build in fertile lowlands near water. Every major civilization in recorded history grew up along a river, a coast, or a combination of both. The Nile, the Tigris and Euphrates, the Indus, the Yellow River, the Rhine, the Thames, the Mississippi. If an advanced coastal society had existed during the last ice age, or during any ice age in the last several 100,000 years, its remains would not be on a hilltop waiting to be excavated. They would be underwater, under 120 meters of ocean, under 12,000 years of marine sediment, in the dark, at depth, on a seafloor that has barely been surveyed. We have looked at a fraction of a percent of the submerged continental shelves of the world. The technology to do this systematically, multi-beam sonar, sub-bottom profiling, autonomous underwater vehicles capable of mapping ancient riverbeds and coastlines at depth, exists now, and has existed for only a few decades. The surveys have not been done. The maps do not exist. We have not looked, and we have declared with considerable confidence that nothing is there. Think about what that means. We are making claims about the completeness of the archaeological record when the most likely location for any prehistoric coastal civilization is sitting under hundreds of feet of water in regions we have not examined. We are reading a book from which the most important chapters may have been dropped into the ocean, and we are telling ourselves the story makes sense. There is a specific site that gives this abstraction a concrete face. Doggerland, the landscape that once connected Britain to the rest of continental Europe, now lying beneath the southern North Sea, has been partially surveyed using commercial fishing trawls and offshore oil drilling cores. What has emerged from that seafloor is extraordinary. River channels, lake beds, the bones of mammoths and aurochs, the remnants of forests, and evidence of Mesolithic human habitation across a landscape that has been underwater for roughly 8,000 years. People lived there, they hunted there, fished there, built fires there, and then the sea took it, and for most of human history, no one knew it had ever existed. That is one site, partially surveyed, in one part of the world. Multiply it by every continental shelf on every ocean, and you begin to get a sense of the scale of what we have not yet seen. The planet is not hiding things from us deliberately. It is simply doing what it has always done, cycling, eroding, subducting, flooding, indifferent to whether the evidence it destroys might have mattered to a species that would not arrive to look for it for another 50 million years. But we are here now, and we are only just beginning to develop the tools to look in the right places. What we have been looking at for the last 2 centuries of serious geological science is the fraction of the record that survived, the rocks that made it through, the chemical signals that were not overprinted or dissolved or subducted. And in that surviving fraction, there are anomalies, real ones, events that do not fit neatly, moments in the deep record where something happened that our best explanations have not fully accounted for. The most striking of those moments is encoded in a thin layer of sediment from 56 million years ago. It runs through cores pulled from dozens of locations around the world, and it tells a story about the Earth's atmosphere and oceans that is, if you know what you are looking at, deeply familiar. It looks like us. The name scientists use for it is the Paleocene-Eocene thermal maximum. Most researchers in the field simply call it the PETM. It sits in the geological record at a depth corresponding to roughly 56 million years ago, and if you know what you are looking for, it is not subtle. In core after core, from the bottom of the Atlantic to the frozen sediments of the Arctic, the same signature appears: a sudden, sharp shift in the chemistry of the rock, a brief and violent departure from everything that came before and after, and then a long, slow return to something resembling normal. It is the largest and most abrupt warming event in the last 65 million years, and it has a feature that, once you understand it, is difficult to set aside. It looks almost exactly like what we are doing to this planet right now. Here is what the record shows. Over a period that geologists estimate at somewhere between 6,000 and 20,000 years, which sounds long in human terms but is a geological eye blink, the equivalent of a few minutes in that compressed 24-hour day, an enormous quantity of carbon entered the Earth's atmosphere. The estimates vary depending on the method used and the assumptions built into the models, but the figures that emerge from the most careful analyses suggest somewhere between 3,000 and 13,000 petagrams of carbon were released. A petagram is a billion metric tons. Sit with that number for a moment. To put it in proportion, since the beginning of the Industrial Revolution, humanity has released roughly 600 petagrams of carbon into the atmosphere. The PETM released, at the most conservative estimate, 5 times that amount. At the upper end of the range, it may have released more than 20 times as much. In a period of time that, from the Earth's perspective, was almost instantaneous. The consequences were not subtle. Global average temperatures rose by somewhere between 5 and 8 degrees Celsius. That range does not sound dramatic until you understand what it means for a living planet. The entire scientific and political conversation about modern climate change is focused on preventing a rise of 1.5 to 2 degrees. 5 to 8 degrees is a different world entirely. Not a warmer version of the one we know, but a fundamentally reorganized planet operating under different rules. The Arctic Ocean reached temperatures of approximately 23 degrees Celsius. That is warmer than the Mediterranean in summer. Subtropical conditions extended to within a few degrees of the poles. Crocodile relatives lived above the Arctic Circle. Palm trees grew in what is now northern Canada. The tropics, already warm, became so hot that many species that had thrived there were simply unable to survive. The equatorial regions became a thermal barrier, rather than a cradle of diversity. In the oceans, the consequences were catastrophic. As the atmosphere warmed and carbon dioxide dissolved into seawater, the chemistry of the oceans shifted toward acidity. Carbonate chemistry is the foundation of marine life in ways that are easy to underestimate. The shells of countless organisms, the skeletons of corals, the structures of the creatures that live on the deep sea floor, all depend on the ocean's ability to maintain the right chemical balance for calcium carbonate to form and hold together. When that balance tips, shells dissolve. Organisms that cannot adapt quickly enough simply die. The deep ocean lost oxygen. The technical term is anoxia, a state of oxygen depletion that turns the bottom of the sea into a near-dead zone. Creatures that had lived on the deep sea floor for millions of years were wiped out in what the fossil record records as the largest deep-sea mass extinction event of the last 93 million years. An entire ecological layer gone. On land, the disruption was no less severe. Rainfall patterns shifted violently. Regions that had been lush became arid. Others were hammered by storms of an intensity the landscape had not seen before. The fossil record of the Bighorn Basin in Wyoming, one of the most detailed terrestrial records of this period anywhere in the world, shows a wholesale reorganization of the mammalian fauna. The paleontologist Philip Gingerich, who spent decades working those rocks, documented sudden disappearances of established species and the equally sudden appearances of entirely new ones. The landscape was rebuilt from the ground up, and then, over the following 100 to 200,000 years, the Earth slowly recovered. Carbon was drawn back down, partly through the weathering of silicate rocks, partly through the burial of organic matter in sediments, partly through the regrowth of forests and the gradual absorption of carbon dioxide by the cooling oceans. Temperatures fell. The chemistry of the sea normalized. Life adapted, diversified, and moved on. What remained was the scar, a thin band of chemically anomalous rock pressed between layers of ordinary sediment, preserved in cores and outcrops around the world, waiting for a species with the tools and the curiosity to find it and ask what it meant. The question of what it means, what actually caused it, is where the science gets genuinely complicated, and where, if you are willing to follow the logic carefully, things become uncomfortable. There are three leading hypotheses for what triggered the PETM, and they are not mutually exclusive. Most scientists today believe the event was caused by a combination of factors rather than a single mechanism. Understanding each one is important, not because any of them is necessarily wrong, but because their collective inability to fully account for the evidence is itself a significant fact. The first and most widely supported explanation involves massive volcanism associated with the North Atlantic Igneous Province. 56 million years ago, Greenland and Europe were in the process of rifting apart. The North Atlantic was opening, tearing itself wider, and the geological violence of that process produced one of the largest volcanic episodes of the Cenozoic era. Enormous volumes of magma intruded into the sedimentary rocks of the continental margins, and some of those sedimentary rocks were rich in organic carbon, ancient buried organic material accumulated over millions of years. When superheated magma forced its way through those carbon-rich layers, it cooked them, and cooking ancient organic carbon releases it as carbon dioxide and methane, exactly the kind of carbon pulse the PETM record shows. There is supporting evidence for this. Mercury is a reliable geological proxy for volcanic activity. It is released in large quantities during major volcanic episodes and preserved in sedimentary layers. PETM-era sediments in multiple locations show elevated mercury concentrations, consistent with sustained large-scale volcanism. Markus Gutjahr, working at the Guiomar Helmholtz Center for Ocean Research in Kiel, published an analysis in Nature in 2017, arguing that the primary carbon source for the PETM was volcanic, channeled through the North Atlantic Igneous Province. His isotopic modeling suggested that volcanic carbon alone could account for a substantial fraction of the observed excursion. The second hypothesis involves the destabilization of methane hydrates on the ocean floor. Methane hydrates are a form of frozen water in which methane molecules are trapped inside an ice-like crystalline structure. They form in the cold, high-pressure conditions of the deep sea floor and contain truly staggering quantities of methane, a greenhouse gas that, in the short term, is far more potent than carbon dioxide at trapping heat. The deep ocean floor is studded with these structures, and they are stable only within a narrow range of temperature and pressure. If the ocean warms even slightly, the hydrates can melt, releasing their methane in what is called a clathrate gun, a runaway feedback loop in which initial warming triggers methane release, which causes more warming, which releases more methane, which causes more warming still. A clathrate gun releasing even a fraction of the available deep ocean methane could produce exactly the kind of rapid, large-scale carbon pulse the PETM record shows. And the carbon isotope signature of methane from hydrates is consistent with the excursion observed in the rock. This mechanism has the advantage of explaining the speed of the PETM onset, a speed that purely volcanic explanations struggle to account for on their own. The third mechanism is subtler and operates on a completely different timescale. The Earth's orbit around the Sun is not fixed. It varies cyclically in its shape, its tilt, and the direction it points. Changes driven by the gravitational interactions between the planets and described mathematically by the Serbian astronomer Milutin Milankovic in the 1930s. These orbital cycles alter how much solar energy reaches different parts of the Earth at different times of year, and they are the driving force behind the ice ages themselves. Recent research has shown that the onset of the PETM coincided with an extreme configuration of orbital eccentricity and precession, a moment when the Earth was positioned to receive an unusually high amount of solar energy. This orbital push may have been the match that lit the fuse, delivering just enough additional warmth to tip an already unstable carbon system into catastrophic release. None of these mechanisms alone fully explains the PETM. The volcanic hypothesis accounts for a substantial part of the carbon, but struggles with the speed of the onset. The methane hydrate hypothesis explains the speed, but has difficulties with the total magnitude. The orbital hypothesis explains the timing, but cannot by itself produce the observed carbon release. Together, in combination, they explain most of what we see, but not all of it. Here is the detail that sits at the edge of the conversation. The carbon isotope excursion at the heart of the PETM, the shift in the ratio of carbon-12 to carbon-13 that every core sample from this period records, has a specific character. Carbon-13 is the heavier of the two isotopes. Living organisms preferentially use carbon-12, meaning that organic material, things that were once alive, tends to be depleted in carbon-13 relative to inorganic carbon. When organic carbon is released into the atmosphere, the isotopic balance of the entire system shifts in a characteristic direction. The carbon becomes lighter. The ratio shifts negative. Fossil fuels are organic carbon. Coal, oil, and natural gas are the compressed remains of ancient living things. When you burn them, you release their carbon that is depleted in carbon-13, carbon that carries the isotopic signature of its biological origin. The PETM carbon isotope excursion is a negative shift, a release of isotopically light carbon consistent with a biological or organic source, consistent with volcanism releasing carbon from ancient organic sediments, consistent with methane hydrates releasing biogenic methane, and consistent, isotopically, chemically, in terms of its signature in the rock, with the combustion of fossil fuels. Frank and Schmidt made this point with precision, and it is worth making again here with equal precision. They were not arguing that the PETM was caused by an industrial civilization. They stated explicitly that they considered this extraordinarily unlikely. The volcanic and methane hydrate explanations are far more parsimonious. They require no extraordinary assumptions. They draw on well-documented geological mechanisms, and they are supported by multiple independent lines of evidence. But the point they were making is this. If an industrial civilization had existed 56 million years ago and had burned through the fossil fuel reserves available to it over the course of a few thousand years, the carbon isotope signature it produced would look, in the geological record, almost identical to what we see at the PETM. The two signals would be, in many core samples, indistinguishable. And there is a deeper irony buried in that observation. Think about what kind of civilization would leave the most detectable trace in the geological record. Not a sustainable one. Not a society powered by sunlight and wind and geothermal energy. Such a civilization would leave almost no chemical signal at all, almost nothing that would stand out from the background noise of the geological record after millions of years. The civilization that leaves the most detectable trace is one that burns vast quantities of ancient organic carbon, one that tips its planet's isotopic balance in a way that persists in the sediment. The more destructive a civilization is to its own environment, the more visible it becomes across geological time. And the most visible kind of destruction, isotopically, chemically, in terms of the signal it leaves in the rock, looks exactly like a volcanic eruption. We look at the PETM and we see a natural event. We apply our best geological tools, and we arrive at explanations that are credible and evidence-based. And in almost every scientific discussion of the PETM, the possibility that it was anything other than a natural event is not on the table. It is not considered. It is not a hypothesis that gets tested and rejected. It is simply outside the frame. Frank and Schmidt's contribution was to ask whether that framing was itself a kind of assumption, whether the confidence with which we read the geological record as a record of purely natural events was earned, or whether it reflected the limits of what our tools were designed to look for. The PETM is not proof of anything except the extraordinary disruption that carbon release causes to a living planet. Its cause is debated, its mechanism is uncertain in its details, and its chemical signature is, by the honest admission of two respected scientists working within the mainstream of their fields, something that a previous industrial civilization would also produce. That is where the story of the rock ends, and the story of what lived on its surface begins. Because the PETM was 56 million years ago. And there is another event, far closer to our own time, whose evidence is not encoded in isotope ratios and sediment chemistry. It is encoded in something more direct, in the bones of vanished animals, in the ruins of a culture that was thriving one day and gone the next, in the chemistry of a boundary layer that contains materials which should not exist, materials that the Earth does not produce on its own. Something struck this planet 12,800 years ago, or exploded above it. The details are still being argued, but what happened immediately after is not in serious dispute. The world changed, catastrophically, and suddenly, and it may have taken with it something we have spent most of human history not knowing existed. Picture the world 12,800 years ago. The great ice sheets that had buried much of North America and northern Europe under kilometers of glacial ice for tens of thousands of years are in retreat. The climate is warming. Sea levels are rising steadily as that ice melts and returns to the oceans. The planet is in the early stages of what would eventually become the world we know, the temperate, relatively stable climate of the Holocene, the geological epoch in which all of recorded human history has taken place. But that world has not arrived yet. What exists is a transition, a hinge point between the frozen world of the Ice Age and the warmer world that follows. And in that transition, life on every continent is doing what life does, adapting, expanding, filling the spaces the retreating ice has opened up. In North America, the landscape is extraordinary. Vast grasslands and open forests stretch from the Gulf of Mexico to the margins of the ice. And moving through those landscapes are animals that no living person has ever seen. Woolly mammoths, standing nearly 4 meters tall at the shoulder, moving in family groups across the tundra. Mastodons, heavier and more heavily built, browsing in the forests. Giant ground sloths the size of modern elephants, rearing on their hind legs to pull branches from trees. Short-faced bears, taller than grizzlies and built for speed. American lions, larger than their African relatives. Saber-toothed cats with canine teeth the length of a human hand. American horses and camels, yes, camels, native to North America long before they were associated with deserts on the other side of the world. Dire wolves, hunting in packs. Giant beavers the size of black bears. A megafauna of extraordinary diversity and richness. Moving through this landscape too are people. The Clovis culture, named for a site near Clovis, New Mexico, where their characteristic stone tools were first identified in the 1930s, represents some of the most sophisticated stone tool technology in the prehistoric world. Their spear points are remarkable objects, carefully fluted, symmetrical, beautifully made, designed for penetration and attached to wooden shafts for throwing. They were hunters, skilled and mobile, following the herds across a continent that had never before seen human beings. The world is opening up. The ice is retreating. The future, from where the Clovis people stand, looks wide. And then, in what the geological record suggests, was the span of a human lifetime, perhaps less, everything changes. The megafauna of North America vanish, not gradually, not through the slow attrition of climate shift or overhunting spread across millennia. They disappear from the fossil record at a horizon that is, in geological terms, simultaneous. 35 genera of large animals gone: mammoths, mastodons, ground sloths, short-faced bears, American lions, saber-toothed cats, dire wolves, horses, camels, all of them absent from the layers above a specific stratigraphic line. An entire ecological community erased. The Clovis culture vanishes at the same moment. Their distinctive tools, those carefully crafted fluted points, disappear from the archaeological record. What appears in the layers above is different, simpler. The continuity is broken. Whatever knowledge and craft and tradition produced those points was not passed on in the same form. Something interrupted the thread, and the climate, the steadily warming climate that had been driving the retreat of the ice for thousands of years, abruptly reverses. Temperatures that had been rising for millennia suddenly plummet. In Greenland, Ice core records show temperature drops of as much as 10 to 15 degrees Celsius within what appears to be decades. The warming stops, winter returns. The period that follows, lasting roughly 1,200 years, is one of the coldest episodes of the last 20,000 years. Scientists call it the Younger Dryas. The name comes from Dryas octopetala, a small white Arctic flower whose pollen, preserved in the sediment record, suddenly reappears in European deposits that had previously recorded warm-loving plant communities. The flowers came back. That is how cold it got. The conventional explanation for the Younger Dryas cooling has existed for decades and remains the position of most mainstream climatologists. As the North American ice sheets melted, meltwater drained into the Atlantic through rivers and drainage systems. At some point, a massive glacial lake, Lake Agassiz, an inland sea of meltwater that at its peak covered an area larger than all of the modern Great Lakes combined, catastrophically drained. An enormous pulse of cold, fresh water poured into the North Atlantic. Fresh water is less dense than salt water. When it floods into the North Atlantic in sufficient quantities, it disrupts the thermohaline circulation, the system of ocean currents that moves warm tropical water northward and keeps Europe and the North Atlantic region warmer than their latitude would otherwise allow. Shut down that circulation, and you shut down the heat supply. Europe freezes. The effects ripple globally. The Younger Dryas begins. This explanation is coherent. It is supported by oceanographic evidence. It accounts for the cooling pattern in the climate record, but it does not explain the megafaunal extinction. A freshwater pulse into the North Atlantic, however catastrophic, does not kill every mammoth on the continent. It does not explain why animals that had survived multiple previous glacial cycles, creatures that had evolved over millions of years to cope with cold, suddenly disappeared at this particular moment. And it does not explain what is found in the sediment at the boundary layer itself. What is found in that layer should not be there. In 2007, a team of roughly 24 researchers, led by Richard Firestone of the Lawrence Berkeley National Laboratory, presented their findings at the American Geophysical Union. They had been studying sediment layers from sites across North America, archaeological sites, geological exposures, lakebed cores, all dating to the Younger Dryas boundary. And at every site, within the same thin stratigraphic layer, they found the same set of materials: nanodiamonds, microscopic diamonds, smaller than a human red blood cell, that form only under conditions of extreme temperature and pressure, the kind produced by a large cosmic impact or a high-altitude explosion. They are not produced by volcanism. They are not produced by any known terrestrial process. They form when carbon is subjected to pressures and temperatures that do not occur naturally on the Earth's surface. Magnetic microspherules, tiny metallic spheres that form when rock or soil is flash melted by an intense thermal event, and the molten droplets resolidify in mid-air before falling back to the ground. They appear at known impact sites and in the debris fields of nuclear weapons tests. They are not a common feature of ordinary sediment. Elevated iridium concentrations. Iridium is extraordinarily rare in the Earth's crust. It sank into the planet's core during formation. But it is relatively abundant in asteroids and comets. High iridium concentrations in sediment layers are one of the key signatures of major cosmic impacts. The same signature that marks the end of the Cretaceous, 66 million years ago, when the impactor that ended the dinosaurs left its iridium fingerprint in rock around the world. Shocked quartz. Grains of quartz mineral showing internal fracture patterns produced only by extreme pressure events, pressures that do not occur in ordinary geological processes. They occur in nuclear detonations. They occur in cosmic impacts, carbon spherules and soot, evidence of biomass burning on a scale consistent with continent-wide wildfires. Fires whose smoke and debris would have blocked enough sunlight to suppress photosynthesis and trigger rapid cooling across the hemisphere. At over 50 sites across North America, and at additional sites in Europe, the Middle East, and South America, this same assemblage of materials appears at the same stratigraphic level, the same thin layer, the same moment in time. Firestone and his colleagues proposed that a large, low-density extraterrestrial object, most likely a fragmenting comet, had exploded over or impacted the northern hemisphere, most probably over the Laurentide ice sheet covering much of North America. An airburst of this kind would not necessarily leave a conventional crater. The Tunguska event of 1908 gives us a scaled reference point. A relatively small object, perhaps 60 meters across, exploded in the atmosphere above Siberia and flattened approximately 2,000 square kilometers of forest without leaving any impact crater at all. The Younger Dryas impactor, if it existed, would have been orders of magnitude larger. The energy released would have been equivalent to thousands of nuclear weapons detonating simultaneously. The effects would have been immediate and cascading. The thermal pulse from the airburst would have ignited forests across a vast area, producing the continent-wide wildfire evidence that Wendy Woolbach of DePaul University documented in 2018. One of the largest biomass burning episodes in the last 125,000 years, recorded in charcoal, soot, and carbon deposits at the boundary layer around the world. The shockwave would have devastated everything within its radius. The debris and soot thrown into the upper atmosphere would have dimmed the sun and triggered rapid cooling. And the impact over or near the ice sheet would have destabilized it, releasing the meltwater pulse into the Atlantic that disrupted the ocean's circulation. One event, every consequence explained. The reaction from the scientific community was intense, and the debate has not resolved cleanly. Critics challenged the nanodiamond identifications, arguing that the analytical methods were insufficiently rigorous. Proponents refined their techniques and found nanodiamonds at additional sites using multiple independent approaches. Critics questioned whether the microspherules were truly of cosmic origin. Proponents pointed to their chemical composition, their morphology, and their global distribution. Critics argued that the boundary layer did not appear consistently across all proposed sites. Proponents expanded the survey and found the assemblage at more than 50 locations across 4 continents. The mainstream consensus still leans toward the freshwater pulse hypothesis for the Younger Dryas cooling. The impact hypothesis remains contested, but it has not gone away, and in recent years, the evidence has continued to accumulate. In 2020, Andrew Moore and colleagues published findings from Abu Huraira in Syria, one of the earliest agricultural settlements ever found, occupied by people in the process of transitioning from hunting and gathering to deliberate plant cultivation. The destruction layer at Abu Huraira contains glass formed at temperatures exceeding 2,200 degrees Celsius. That temperature does not occur in ordinary fires. It does not occur in any known volcanic process. It occurs at nuclear test sites, where the detonation fuses soil into glass. It occurs in cosmic impacts. The people of Abu Huraira, some of the earliest farmers in human history, were living in a village that was, by the physical evidence preserved in its ruins, caught in the thermal pulse of an event that should not have been possible. And then there is Greenland. In 2018, a team led by Kurt Kjær of the Natural History Museum of Denmark, using airborne radar surveys, identified a massive impact structure buried beneath the Hiawatha Glacier in northwest Greenland. The crater is 31 kilometers wide, larger than the city of Paris. A central uplift at its center indicates the signature of a high-velocity impact. Initial dating suggested an age that fell within the Younger Dryas window. Subsequent research has pushed the estimated age somewhat further back, and the question of whether the Hiawatha crater is directly related to the Younger Dryas boundary event remains actively debated. But here is what the Hiawatha crater proves, regardless of its precise age. A large cosmic impact occurred in the northern hemisphere during the relevant geological period. There is a 31-kilometer hole under the Greenland ice. Something real made it. Think about what this kind of event would have meant for everything alive on the surface. Not a gradual process. Not a slow climate shift that organisms have centuries to adapt to. A sudden, violent catastrophe. Fire and cold and darkness arriving within a human lifetime, perhaps within a human year. The megafauna did not adapt because there was no time to adapt. The Clovis culture did not continue because whatever remained of it after the fires and the cold and the collapse of the prey animals it depended on was not the same thing that had existed before. And if there was something more, if the people living through the end of the Ice Age were more organized, more connected, more sophisticated than the standard narrative allows, then the Younger Dryas event did not merely end a culture. It may have ended a chapter of human history for which we have barely begun to find the evidence. Because here is the question the impact hypothesis raises, and the conventional narrative has no satisfying answer for. Where was human civilization in 12,800 BCE? The standard answer is small bands of hunter-gatherers, living in temporary camps, leaving almost no permanent mark on the landscape. But that answer was given before a particular hilltop in southeastern Turkey was properly excavated, before a particular set of limestone pillars emerged from the earth, before a radiocarbon date came back from the laboratory and forced everyone who received it to sit quietly and reconsider everything they thought they knew. That hilltop has a name, and what was built there, by people who, according to everything else we knew about them, should not have been able to build anything like it, is where this story goes next. In 2018, a team of researchers led by Kurt Kjær of the Natural History Museum of Denmark published a discovery that changed the terms of the Younger Dryas debate in a single paper. They had found a crater, not on a distant planet, not on the surface of the moon, under the ice of Greenland, buried beneath 3,000 feet of glacial ice that had hidden it from every survey and every satellite and every human eye since the moment it formed. A circular depression in the bedrock, 31 kilometers wide, with a raised central structure, the signature of a high-velocity impact, the same feature you see in craters on the Moon and Mars, formed when the energy of the strike rebounds upward through the target rock like a slow-motion wave. 31 kilometers wide, larger than the city of Paris. Sitting under the Hiawatha Glacier in northwest Greenland, undetected until a team of glaciologists analyzing airborne radar surveys of the ice sheet noticed an anomaly in the shape of the bedrock beneath them and followed it to its conclusion. The discovery process itself is worth understanding because it speaks to how much of the planet we have simply not looked at. The Hiawatha crater was not found by a dedicated search for impact structures. It was found, incidentally, by researchers using ice-penetrating radar flown on aircraft to map the landscape buried under the Greenland ice sheet. The radar pulses travel through the ice and bounce back off the bedrock below, building up a picture of what the surface looks like under kilometers of glacial cover. The team noticed that the bedrock in this region was not flat. It dipped in a circular pattern. Sediment analysis from meltwater rivers draining the glacier revealed shocked quartz grains bearing the internal fracture patterns that only extreme impact pressure produces, along with other materials consistent with a cosmic strike. The crater had been there the entire time, waiting under the ice. Nobody had thought to look. The initial age estimates placed the impact within the last 800,000 years, with some analyses suggesting it could be as recent as 12,000 years ago, placing it squarely within the window of the Younger Dryas boundary event. Subsequent dating work has produced a wider range of possible ages, and the debate about when, precisely, the Hiawatha impact occurred is ongoing. Some analyses lean toward an age that predates the Younger Dryas by a significant margin. Others remain consistent with a more recent strike. The precision required to settle the question is at the outer limits of what current dating methods can reliably deliver for an impact buried under kilometers of ice, with the impacted surface inaccessible to direct sampling. What is not debated is the physical reality of the structure itself. The crater is there. It is large. The evidence of the impact, the shocked minerals, the deformation of the bedrock, the central uplift, is unambiguous. And its existence in the Northern Hemisphere, in a region covered by the Laurentide and Greenland ice sheets during the Ice Age, is a documented geological fact rather than an inference from proxy evidence in sediment cores. This matters beyond the specific question of whether Hiawatha caused the Younger Dryas. It matters because one of the most persistent objections to the Younger Dryas impact hypothesis has been that a large impact would leave a crater, and no crater had been found. The standard counter-argument that a fragmenting comet or a porous, low-density impactor could deliver its energy primarily as an airburst without forming a conventional crater is well supported by physics and by the evidence of events like Tunguska. But the absence of any confirmed crater in the relevant region had been used, repeatedly, to suggest the hypothesis lacked a physical anchor. The Hiawatha crater removes that objection. It does not prove that the Hiawatha impact caused the Younger Dryas. The age uncertainty is real, and intellectual honesty requires acknowledging it, but it proves that the Northern Hemisphere experienced a very large cosmic impact during a period that overlaps with, or is at minimum geologically adjacent to, the Younger Dryas boundary. The hypothesis that such events occur is no longer hypothetical. It is documented, and Greenland is not the only recent addition to the physical evidence. In 2025, researchers published findings from a site in Louisiana, a crater-like depression nearly 1,000 feet across in the landscape of the American South, identified during geological survey work. The site contained the same suite of impact proxy materials found at Younger Dryas boundary sites elsewhere. Magnetic microspherules, shocked quartz, and glass formed at temperatures exceeding 2,000 degrees Celsius. The characteristics of that glass matched materials produced at nuclear test sites in New Mexico and Kazakhstan, where atomic detonations had fused the local soil and rock into similar structures. There is no natural process operating at the Earth's surface that produces glass at those temperatures. The list of mechanisms that can is very short, and it ends with cosmic impact. The Louisiana site adds to a growing catalogue of physical locations, where the signature of the Younger Dryas boundary event is not just a chemical trace in a sediment core, but a feature in the landscape, a place you can stand in, a structure you can measure, material you can hold in your hand and submit to analysis. Meanwhile, deep in the ocean, a different kind of conformation was building. Sediment cores pulled from the floor of Baffin Bay, the body of water sitting between Greenland and the Canadian Arctic archipelago, were found to contain silica-rich and iron-rich microspherules at the same stratigraphic level as the Younger Dryas boundary on land. The ocean floor is a remarkably faithful archive of atmospheric and surface events. Material that falls into the sea, dust, debris, spherules formed in impact events, settles through the water column and is preserved in the accumulating sediment. Finding the impact proxy signature in marine sediment cores provides an independent line of evidence entirely separate from the terrestrial sites. It is the ocean saying in its own language, something happened here, and it happened at this moment. Taken together, the Hiawatha crater, the Louisiana airburst site, the Abu Huraira destruction layer, the marine sediment evidence, and the original suite of impact proxies from over 50 terrestrial locations across 4 continents. The Younger Dryas impact hypothesis has a physical foundation that is considerably more substantial than its critics initially allowed. The debate continues. The mainstream has not reached consensus. There are researchers who remain unconvinced, and their objections are not without merit. Science is not settled by accumulation alone. It requires the weight of evidence to tip decisively in one direction, and that tipping has not yet occurred. But the direction of travel is clear. Each year, new sites are added to the global distribution map of the boundary layer. Each new find extends the geographical range of the evidence. Each new dating result tightens the temporal window. And each physical structure, each crater, each glass-fused soil horizon, each marine microspherual layer, makes the hypothesis harder to dismiss on the grounds that it lacks a material record. What the evidence is building toward, not as a certainty, but as an increasingly compelling possibility, is a picture of the Northern Hemisphere at 12,800 years before the present, as a place undergoing catastrophic disruption on a scale that no gradual process can account for. Fire across a continent. Darkness following the smoke. Cold following the darkness. The collapse of an entire ecological community. And with it, the collapse of the cultures that depended on that community. Whatever was living through that event did not have the luxury of a slow adjustment. Whatever was building, whatever was learning, whatever was accumulating knowledge and skill and connection across the Ice Age world, it was interrupted, abruptly and violently. The question is not just what was destroyed. The question is what was there to be destroyed. Because 1,200 kilometers to the southeast of the Hiawatha crater, on a ridge of limestone hills in southeastern Turkey, the answer to that question is emerging from the ground one excavation season at a time. And it is an answer that the archaeology of the last 30 years has not found a comfortable way to absorb. 15 kilometers northeast of the ancient city of Şanlıurfa in southeastern Turkey, the land rises in a series of low limestone ridges worn smooth by thousands of years of farming and weather. The hills here are unremarkable to the eye. Dry grass, scattered stones, the occasional fig tree. Farmers have worked this soil for generations. And for generations, they noticed the stones. Worked stones, shaped stones, fragments of carved rock turning up in the earth when they ploughed. They stacked them along the edges of their fields and forgot about them. In 1963, a joint survey team from Istanbul University and the University of Chicago visited the site. They recorded it in their notes as a medieval cemetery. The worked stones, they concluded, were grave markers. They moved on. For 31 years, what would eventually be recognized as the most important archaeological discovery of the 20th century sat in a Turkish farmer's field, dismissed, ignored, and slowly being damaged by the agricultural activity above it. Then, in 1994, a German archaeologist named Klaus Schmidt arrived. Schmidt had been working at another prehistoric site in the region called Neveli Chori and was actively searching for additional sites of similar antiquity. Local people directed him to the hilltop. He walked across the ridge, looked at the stones that had been there the entire time, and recognized them immediately for what they were. These were not medieval. They were not grave markers. They were prehistoric, and they were old, far older than anything the region had previously yielded. He began excavating the following year. And what emerged from beneath the soil of that unremarkable Turkish hilltop was so unexpected, so structurally impossible, given everything the archaeological world thought it knew about this period of human history, that it took years for the full implications to settle into the discipline. The site is called Göbekli Tepe. In Turkish, the name means Potbelly Hill. It is the oldest monumental structure on Earth. What the excavation revealed was a series of enclosures, circular arrangements of massive T-shaped limestone pillars, some standing nearly 5 meters tall, some weighing as much as 20 tons, set into carefully constructed walls of smaller stones. The pillars are not rough-hewn. They are precisely shaped, their surfaces worked smooth, their T-forms, which appear to represent the heads and shoulders of stylized human figures, with carved arms running down the sides of some pillars and hands clasped at the front, executed with a degree of craft that implies not just technical skill, but artistic intention. The carvings that cover many of the pillars are extraordinary. Foxes, wild boars, lions, vultures, scorpions, snakes, spiders, gazelles, aurochs, a bestiary rendered in high relief across the faces of the stone with a naturalism and energy that would not embarrass a sculptor working several thousand years later. Interspersed with the animals are abstract symbols, H-shapes, crescents, circles, forms that no one has yet fully decoded. The entire program of imagery speaks of a symbolic world of considerable complexity, a visual language shared by the people who built and used these enclosures, expressing ideas about the relationship between human beings, animals, and whatever forces governed the world they lived in. 20 such enclosures have been identified through ground-penetrating survey of the site. Only a fraction have been excavated. The full extent of what lies beneath the hill is still unknown. The radiocarbon dating of organic material from the oldest layers of the site placed the construction of the earliest enclosures at approximately 9,500 years before the Common Era, 11,500 years ago. That date requires a moment of stillness. 11,500 years ago. More than 6,000 years before Stonehenge. More than 6,000 years before the construction of the Egyptian pyramids. Older than any permanent human structure previously known to exist anywhere on Earth. Older than pottery. Older than metalwork. Older than the wheel. Older than writing. Built before the first city. Before the first domesticated grain crop was cultivated at scale. Before any of the foundations we associate with organized civilization had been laid. And built. This is the part that the conventional model of human development has never satisfactorily absorbed, by people who, according to every other line of archaeological evidence from this period, were hunter-gatherers, people with no permanent villages, no agriculture, no surplus food production, no social hierarchy built on accumulated wealth, no writing system, no metal tools, flint, bone, wood. That is what they had. With those tools, they quarried limestone blocks weighing up to 20 tons from outcrops several hundred meters away. They shaped those blocks into precise T-forms. They transported them to the hilltop. They erected them in carefully planned circular arrangements. They covered them with sophisticated carved imagery. And they did this not once, as a single burst of collective effort, but repeatedly, enclosure after enclosure, century after century, across a construction program that lasted thousands of years. The organizational scale this implies is staggering. Moving a 20-ton limestone pillar without wheeled vehicles, without draft animals, across uneven terrain requires a coordinated effort involving dozens of people working together with a shared plan. Doing it repeatedly, over generations, requires something more than a seasonal gathering. It requires leadership, communication, specialized knowledge passed from one generation to the next, and a social structure capable of directing collective labor toward a long-term goal. None of that fits the textbook picture of a hunter-gatherer band. A study published in the Cambridge Archaeological Journal examined the spatial layout of 3 of Göbekli Tepe's main enclosures and found that their positions are not arbitrary. The 3 enclosures are connected by an equilateral triangle, a geometric relationship that is not accidental and that implies the entire complex was conceived as a unified design rather than a series of separate structures accumulated over time. The builders used ropes to measure distances and establish angles. They planned the site before they built it. They had, in other words, a blueprint. This is not the behavior of people who wandered onto a hilltop and started stacking stones. This is the behavior of people who knew what they were doing. The implications of Göbekli Tepe reach in several directions at once, and it is worth following each of them carefully. The first is the question of how this was possible at all. Where the knowledge and organizational capacity to build something like this came from, if the standard model of human prehistory is correct, and the builders were indeed pre-agricultural hunter-gatherers with no prior tradition of monumental construction to draw on. Klaus Schmidt, who spent the rest of his career excavating the site until his death in 2014, proposed an answer that has become influential in the archaeology of the Neolithic transition. His argument was essentially this: Göbekli Tepe did not emerge from an agricultural society. It created one. The construction and maintenance of the site required a labor force far larger than any single hunter-gatherer band could provide. To gather enough people in one place, to feed them while they worked, to sustain the effort across months and seasons, the organizers of Göbekli Tepe would have needed food in quantities that opportunistic hunting and foraging could not reliably deliver. The pressure to feed the workforce, Schmidt argued, was the catalyst for deliberate plant cultivation. The temple did not come after farming, it came before it, and it created the conditions that made farming necessary. There is evidence to support this. 20 miles from Göbekli Tepe, geneticists identified the world's oldest domesticated strains of wheat. The radiocarbon dates place this domestication at approximately 10,500 years before the Common Era, 500 years after the construction of Göbekli Tepe began. The cradle of agriculture and the world's oldest temple are near neighbors. The sequence is precisely what Schmidt predicted. The second implication concerns the deliberate burial of the site. Around 8,000 years before the Common Era, After the enclosures had been in use for more than 1,000 years, the people who had built and maintained Göbekli Tepe filled it in. Deliberately, systematically, using earth, rubble, and refuse. They did not abandon it and let nature reclaim it slowly. They actively covered it, enclosure by enclosure, with material that suggests organized effort rather than simple neglect. Why? Nobody has a satisfying answer. Ritual closure is one possibility. The symbolic end of a religious era, the sealing of sacred space when its function had been fulfilled or superseded. Deliberate concealment is another, hiding the site from enemies or from a new generation with different beliefs. Some researchers have noted that the material used to fill the enclosures contains animal bones, stone tools, and fragments of carved stone, suggesting the burial was not a hasty act, but a considered one, carried out by people who understood what they were covering over. Whatever the reason, the burial was, intentionally or not, an act of extraordinary preservation. Without it, 12,000 years of erosion, seismic activity, and agricultural disturbance would have reduced Göbekli Tepe to rubble, indistinguishable from the hillside around it. The people who buried it, for whatever reason, gave the future the ability to find it. That is not nothing. The third implication is the one that sits most uncomfortably with the conventional timeline. If hunter-gatherers could build Göbekli Tepe, if the organizational capacity, the symbolic intelligence, the geometric planning, and the technical skill required to construct this site were all present in human beings 11,500 years ago, then the standard narrative of gradual linear progress from simple to complex is wrong, or at least incomplete. The question it raises is not just what else they could build, it is what else they might have built that we have not found, or that was destroyed, or that is sitting right now underwater on a continental shelf that has never been surveyed. And there is one more thread that cannot be left unexamined. On one of the most elaborately carved pillars at Göbekli Tepe, designated Pillar 43, known informally as the Vulture Stone, a complex scene is carved in high relief. A vulture holds a circular object in one wing. Below it, a headless human figure. Around them, a scorpion, a crane, and other animals arranged in a composition that has the density and deliberateness of a narrative image rather than a decorative one. Martin Sweatman and Dimitrios Tsikritsis of the University of Edinburgh published an analysis of this image in 2017, proposing that the animals on the Vulture Stone correspond to constellations as they would have appeared on the horizon at specific times of year, and that the composition encodes a specific astronomical date using the precession of the equinoxes. The slow wobble of the Earth's rotational axis that shifts which stars appear were in the sky over a cycle of roughly 25,700 years. Their analysis identified the encoded date as approximately 10,950 years before the Common Era. That date is the onset of the Younger Dryas. If Sweatman and Tsikritsis are right, and their interpretation remains debated within archaeoastronomy as it should, then Pillar 43 is not just a carved stone, it is a record, a message, a way of saying, this is when the sky changed. This is when the world we knew ended. We are marking this moment in stone so that something of it survives. You do not record a date in stone unless you have a reason to remember it. The timing of Göbekli Tepe's construction, beginning immediately after the Younger Dryas cold period ended, has always been striking. The oldest structures date to approximately 11,500 years ago. The Younger Dryas ended at approximately 11,600 years ago. The gap between the end of one of the most severe climate disruptions in human prehistory and the beginning of construction at the world's oldest monumental site is, in archaeological terms, negligible. It is as if the moment the cold released its grip on the world, the moment the sky cleared and the earth warmed and the long darkness finally lifted, someone began building immediately, urgently, with a level of skill and knowledge that does not suggest they invented it from scratch in the aftermath of a catastrophe. Which raises the question, that no archaeology textbook has yet found a comfortable place for. Where did that knowledge come from? The answer to that question may lie not in the stone, but in the stars, in the slow drift of the sky over thousands of years, and in a geological feature of a very famous monument in a very different part of the world, one that has been sitting in a desert, staring east, for longer than anyone has been willing to admit. The Giza Plateau sits at the edge of the Sahara Desert, 9 miles west of Cairo, on a limestone shelf that rises above the Nile floodplain. It is one of the driest places on Earth. Annual rainfall averages less than an inch. The dominant weathering agents are wind and sand, the constant abrasion of airborne particles carried by desert winds across a landscape that has been essentially arid for the last 5,000 years. On that plateau, facing due east toward the rising sun, sits the Great Sphinx. Its body is the length of a city block. Its head rises higher than a 4-story building, and it was carved, not built, directly from the living bedrock of the plateau. The engineers who made it did not assemble it from blocks. They cut downward into the rock from above, liberating the form from the stone that surrounded it, leaving a rectangular enclosure around the body and the figure standing at the center. The conventional dating places its construction at approximately 2,500 years before the Common Era, during the reign of Pharaoh Khafra, builder of the second largest pyramid at Giza. The evidence for this attribution is circumstantial. The Sphinx's proximity to Khafra's pyramid complex, its stylistic similarity to Old Kingdom artistic conventions, and a fragmentary stela positioned between its paws that may reference Khafra's name. Though the relevant section of the text is badly eroded and the reading is not universally accepted. There is no inscription on the Sphinx that names its builder. No contemporary record of its construction has ever been found. For most of the 20th century, this dating was accepted without serious challenge. Then, in 1990, a geologist walked into the Sphinx enclosure and saw something that no one working within Egyptology had apparently stopped to consider. His name was Robert Schoch. He held a doctorate in geology and geophysics from Yale University and was an associate professor at Boston University. He was not an Egyptologist. He had not been looking for a lost civilization. He had been invited to Egypt by an independent researcher named John Anthony West, who had long suspected that the conventional dating was wrong and wanted a geologist to examine the rock. Schoch went, expecting to spend a few days and confirm what everyone already believed. It took him moments to see the problem. The walls of the Sphinx enclosure, the vertical faces of the trench carved into the bedrock when the Sphinx's body was freed from the surrounding limestone, showed a pattern of erosion that Schoch recognized immediately from his training and fieldwork. Deep, rounded, vertical channels, undulating surfaces that were wider at the top than at the bottom. A profile produced by one specific weathering process and no other. Water running down vertical surfaces over extended periods, dissolving and removing the softer limestone layers, carving characteristic rounded grooves from above. Rainfall erosion on a structure in the middle of a desert. The other rock-cut structures on the Giza Plateau, the tombs and temples of Khafra's era, carved from the same geological formations at the same time, according to the conventional timeline, showed a completely different erosion pattern. Horizontal striations, sharp edges, angular surfaces, the characteristic signature of wind and sand abrasion, consistent with several thousand years of desert conditions. If the Sphinx and those other structures had been carved at the same time from the same rock, they should show the same erosion patterns. They do not. The erosion on the Sphinx enclosure walls is not a variation in degree. It is a difference in kind, a different process, and different processes operating on the same rock type over the same duration do not produce such fundamentally different profiles. The simplest geological explanation, Schoch argued, was that they were not carved at the same time. The Sphinx enclosure had been exposed to rainfall for a period that the other Old Kingdom structures had not. It was older, significantly older, old enough to have been standing during a period when the climate of the Eastern Sahara was substantially wetter than it is today. When was the Eastern Sahara last wet enough to produce the kind of sustained heavy rainfall that would carve vertical channels into limestone? The answer comes from climate science rather than archaeology. Between approximately 12,000 and 5,000 years before the Common Era, the region experienced what geologists call the African humid period, a sustained wet phase driven by shifts in monsoon patterns linked to orbital precession. The Sahara was not a desert. Lakes studded the landscape. Rivers flowed across terrain that is now bone dry. Rainfall was abundant enough to support hippopotamuses, crocodiles, and large human populations across regions that today receive almost no precipitation at all. The rock art of the deep Sahara, images of people swimming, herding cattle, and living beside bodies of water, records this vanished world in ochre on stone. If the Sphinx erosion is the product of that humid period, then the monument was already standing, already old enough to have accumulated significant rainfall damage, before the desert closed in. Schoch's initial estimate placed construction before 5000 before the Common Era. As his research continued, he pushed the estimate further back, suggesting the core body of the monument may date to the end of the last ice age, around 10,000 before the Common Era or earlier. Not 4,500 years old, 12,000 years old, possibly more. The response from mainstream Egyptology was swift and largely dismissive. Mark Lehner, one of the world's leading authorities on the Giza Plateau, rejected the hypothesis on the grounds that it lacked supporting archaeological evidence. You do not overthrow Egyptian history based on one weathering profile, he argued. Other critics proposed alternative explanations. Salt weathering from moisture absorbed by the limestone over millennia, periodic wetting from ancient Nile floods, rainwater seeping through sand that had periodically buried the Sphinx and saturating the enclosure walls from the sides rather than from above. These alternatives have merit and deserve honest assessment. Salt weathering is a real process that operates on limestone in arid environments. The Sphinx has been partially buried by sand for much of its known history, and moisture in that sand could theoretically contribute to the erosion pattern. The geology of the Giza Plateau is not simple, and attributing a weathering profile to a single cause requires ruling out others. Schoch did not dismiss these alternatives. He addressed them. He pointed out that the erosion pattern on the Sphinx enclosure walls shows depth and uniformity consistent with rainfall from above. The channels are widest at the top and taper downward, which is precisely what you expect from water cascading down a vertical surface, and precisely the opposite of what you would expect from moisture wicking upward through sand. He also conducted seismic surveys of the bedrock surrounding the Sphinx, generating sound waves using sledgehammer impacts on steel plates and measuring how those waves reflected off subsurface features. The data showed a depth of subsurface weathering beneath the Sphinx enclosure floor that exceeded what you would expect for a monument only 4,500 years old, and that was consistent with prolonged exposure to weathering from above over a substantially longer period. None of this has settled the debate. Mainstream Egyptology still dates the Sphinx to Khafra's reign, and the counter-arguments to Schoch's interpretation have not been fully answered in either direction. What the geology has established, what cannot be undone by institutional resistance or by the weight of the conventional timeline, is that the question is legitimate. The erosion profile requires an explanation. The subsurface weathering depth requires an explanation. And the explanations that have been offered by those defending the conventional date have not been universally accepted, even among geologists who have no particular stake in the outcome. The Sphinx debate is unresolved. That, in itself, is significant. There is another dimension to the Sphinx that operates entirely independently of the geological argument, and it arrives from a completely different discipline. Look at the Sphinx itself, the body, the proportions, the relationship between the head and the form it sits on. The head is too small, not slightly too small. Measurably, strikingly, disproportionately small relative to the scale of the body. A lion's body of those dimensions should carry a head roughly twice the size of the one currently sitting on it. The disproportion is obvious once you see it, and difficult to unsee. The tool marks on the head are consistent with Old Kingdom craftsmanship, the same techniques and the same period as the other monuments at Giza. The tool marks on the body, where they are preserved at depth in the enclosure walls, are different, older looking, consistent with an earlier phase of work. Schoch and other researchers have proposed that the head was recarved, that whatever the Sphinx originally depicted, its head had been so severely damaged by millennia of exposure that a later pharaoh, perhaps Khafra himself, had the original face carved away and a new one imposed. A smaller head carved from a larger, eroded original would explain both the disproportionate size and the difference in tool marks between the head and the body. The monument you see today is, on this interpretation, two monuments in one: an ancient body built by unknown hands in an earlier era, and a face added by a known pharaoh several thousand years later. This is not a fringe interpretation. It is a coherent geological and architectural hypothesis that follows from the physical evidence, and it would explain something that has always been quietly anomalous about the Giza complex: why the most famous monument on the plateau has no inscription naming its creator, when Old Kingdom pharaohs were not, as a rule, shy about commemorating their achievements in stone. Now bring in the sky. The Earth's rotational axis is not fixed. It wobbles slowly, like a spinning top losing momentum, completing one full wobble every 25,700 years. This wobble, called the precession of the equinoxes, means that the point on the celestial sphere around which the stars appear to rotate shifts gradually over time, and with it, the position of every constellation relative to the horizon at any given moment of the year. The Sphinx faces due east. On the morning of the spring equinox, it stares directly at the rising sun. This orientation is clearly intentional. The monument was built to face the equinoctial sunrise, to greet the moment when day and night are equal and the sun climbs above the eastern horizon at its due east point. But because of precession, the constellation that appears on that eastern horizon at the moment of the spring equinox changes over the centuries. 2,000 years ago, it was Aries. 4,000 years ago, around the time of Khafra, it was Taurus, the bull. Go further back. Rewind the slow wobble of the sky. Reach approximately 10,500 years before the Common Era. The constellation on the eastern horizon at sunrise on the spring equinox was Leo, the lion, a lion monument, facing east, built to greet the equinoctial sunrise. At the moment when the sun rises into the constellation of the lion, the astronomical alignment is precise, the symbolism is not subtle, and the date it points to, 10,500 before the Common Era, falls directly within the window that Robert Schoch's geological analysis proposed for the original construction of the monument. Two entirely independent lines of inquiry, one geological and one astronomical, converging on the same period. This convergence does not constitute proof. Coincidences occur in archaeology and in astronomy, and the precessional alignment argument has been contested on the grounds that the Egyptians of Khafra's era may have had reasons for building a lion-form monument that have nothing to do with the stars. The counter-arguments exist and deserve acknowledgement, but the convergence is real. And convergences from independent disciplines are not nothing. When the rock says one thing and the sky says the same thing, the question deserves to be taken seriously rather than dismissed, because the answer is inconvenient. The picture that emerges from the Sphinx, from its erosion, its proportions, its orientation, its silence on the question of its own origins, is of a monument with a history that does not begin where Egyptology has placed it, of a structure that may have been standing, already ancient, when the pharaohs of the Old Kingdom arrived on the plateau and found it there, of a presence on the Nile horizon that predates the civilization that adopted it, incorporated it, recarved its face, and built their greatest monuments in its shadow. Who built the original? When? And what do they have to do with the people who built a monument in the hills of Turkey at almost exactly the same time, with almost exactly the same level of organizational sophistication? Those questions do not yet have definitive answers. But the people who were asking them, the people who were building and carving and orienting their monuments to the stars at the end of the last ice age, were living on a planet that was simultaneously generating another kind of response to catastrophe. Not monuments above the earth, cities beneath it. In 1963, a man in the town of Derinkuyu in central Turkey was renovating his home. He knocked through a wall in his basement and found darkness on the other side. Not the darkness of a crawl space or a shallow cellar. A deeper darkness. A passage leading downward into the rock. He followed it. The passage led to a room. The room led to another passage. That passage led to another room and another, descending, going deeper, the air growing cooler and the light from the entrance above him fading to nothing. What this unnamed homeowner had broken into was not a cellar, not a medieval storage vault, not anything that had a name in the world he knew. It was a city, an entire city carved from the soft volcanic rock beneath his feet, extending downward through the earth to a depth of approximately 85 meters, 18 levels, and stretching outward through the bedrock of Cappadocia in a network of tunnels, chambers, and shafts that took years of systematic excavation to begin to map. Derinkuyu. The name means deep well in Turkish. It is the largest excavated underground city in the world, and it is one of over 200 known subterranean settlements in the Cappadocia region of central Turkey. It could shelter up to 20,000 people, along with their livestock, along with enough food and water to sustain them for extended periods. What the excavation revealed was not a rough-dug refuge. It was a work of systematic engineering executed to a coherent plan. The ventilation system alone demonstrates this. A network of shafts running from the deepest inhabited levels to the surface provided fresh air throughout the complex. Air circulation so well designed that even at the lowest levels, 85 meters underground, the atmosphere remained breathable. These shafts were not dug as an afterthought. They had to be planned before the first level was excavated because their positioning, their angles, and their diameters were determined by the overall geometry of the complex they were meant to serve. You cannot add a ventilation system to an underground city after it has been carved. You have to design it in from the beginning. Whoever built Derinkuyu knew, before they cut the first stone, how deep they were going and what the finished structure would require. The wells tell the same story. Shafts sinking from the upper levels of the complex down to the water table provided drinking water to the inhabitants without requiring anyone to surface. Again, the positioning of these wells required advanced knowledge of the local geology, specifically where the water table sat relative to the planned depth of the complex. This is not the kind of knowledge you acquire by accident. It is the product of deliberate geological survey and careful planning before construction begins. The defensive architecture is equally deliberate. The corridors connecting the levels of Derinkuyu are narrow, deliberately, functionally narrow. A single person can move through them, but a group cannot move abreast. Anyone attempting to force their way through from one level to another would be channeled into a choke point where a small number of defenders could hold an effectively unlimited number of attackers. At intervals along the corridors, circular stone doors, each weighing several hundred kilograms, each carved from a single piece of rock, could be rolled across the passage from the inside, sealing the level behind a barrier that could not be moved from the outside. Each floor of Derinkuyu could be sealed independently. If the upper levels were breached, the population could retreat deeper, rolling the stone doors closed behind them, withdrawing to the next defended position. This is not improvised. This is military architecture. Strategic thinking applied to an underground environment by people who had worked out, in advance, how an attack on their refuge would unfold and what they would need to survive it. The conventional archaeological explanation for Derinkuyu is straightforward and well supported by historical evidence. Cappadocia sits at the crossroads of empires: Hittite, Persian, Greek, Roman, Byzantine, Arab, Mongol, Ottoman, and control of the region has changed hands repeatedly across 3,000 years of documented history. Historical records confirm that the underground cities were used as refuges during the Byzantine-Arab wars of the 8th through 12th centuries, during the Mongol raids of the 14th century, and as recently as the early 20th century, when Christian communities in the region used the tunnels to shelter from violence during periods of intercommunal conflict. The earliest phases of construction are generally attributed to the Phrygians, who inhabited Cappadocia during the 8th and 7th centuries before the Common Era. The soft volcanic tuff of the region, deposited by ancient eruptions and subsequently hardened into a material that is workable with simple tools, but structurally stable enough to support large underground spaces, made carving feasible in a way that would not have been possible in harder rock. The Phrygians likely began excavating the upper levels, and subsequent cultures, particularly the Byzantine Christians who used the cities most extensively, expanded them dramatically, adding the deeper levels, the chapels, and the more sophisticated defensive features. This explanation is rational. It accounts for the documented historical use of the cities. It does not require any assumptions that go beyond the known archaeological record, but it does not fully account for the scale. 20,000 people, 18 levels, 85 meters deep, a ventilation system that required expert geological and engineering knowledge to design, a defensive architecture that reflects sustained strategic thinking rather than improvised digging, and a network of over 200 such settlements distributed across a region, some of them connected, or believed to be connected, by tunnels stretching kilometers between sites. The tunnel reportedly linking Derinkuyu to the nearby underground city of Kaymakla, 9 kilometers to the north, has never been fully explored. Its full extent is unknown. In 2015, during construction of a housing development near the town of Nevşehir, workers discovered yet another underground city beneath a hilltop castle. Initial surveys suggested it could be larger than Derinkuyu, extending more than 100 meters below the surface and covering an area of nearly 5 million square feet. Less than half of Derinkuyu itself has been excavated. The full scope of what exists beneath Cappadocia remains unmapped. The question that the conventional explanation struggles to fully answer is not who used these cities. The historical record is reasonably clear on that. The question is what the original builders, whoever they were, whenever the deepest and most ancient portions of the complex were first carved, were preparing for. Invasion is the standard answer, and for the historical periods we know about, it is a sufficient answer. A cavalry raid, a marauding army. The logical response is to go underground, seal the doors, and wait it out. A few levels of refuge would serve that purpose adequately. 2 or 3 levels, enough to house the local population and their animals, would be entirely sufficient to survive a raid that lasts days or weeks. You do not need to go 85 meters underground to hide from a cavalry raid. The extreme depth of Derinkuyu, the engineering investment required to go that deep, to ventilate those lower levels, to supply them with water, implies a scenario more severe than a passing army. It implies preparation for a situation in which the surface itself becomes uninhabitable for an extended period. Not dangerous to move through, not risky to emerge into. Uninhabitable. A situation where remaining underground is the only viable option for months, not days. What would make the surface of Cappadocia uninhabitable for months? The geology of the region itself offers one answer. Cappadocia is a volcanically active landscape. The soft tuff that made Derinkuyu possible was deposited by ancient eruptions, massive volcanic events that buried the region under meters of ash and pyroclastic material. The people who lived here were living in the deep shadow of volcanic history. They knew, in whatever way such knowledge was transmitted across generations, that the land beneath them was capable of violence on a scale that erased everything above ground. Going underground during a sustained volcanic eruption, an ashfall that buried the surface, toxic gases that made open air lethal, pyroclastic flows that destroyed everything in their path, is not panic. It is the rational response of people who understood what their landscape could do. This explanation does not require exotic hypotheses. It requires only that the builders of Derinkuyu's deepest levels were thinking about volcanic catastrophe rather than military raids, or both simultaneously, since the two threats are not mutually exclusive. The upper levels serve as military refuges. The deepest levels serve as something more fundamental, a survivable space beneath a surface that might, under sufficiently extreme circumstances, become a place where nothing above ground could live. There is a connection worth making explicit. Göbekli Tepe lies roughly 600 kilometers to the east of Cappadocia. Both regions were inhabited during the same prehistoric period. Both show evidence of remarkable engineering capability at dates that challenge the conventional model of what pre-agricultural humans were able to do, and both exist in a volcanic landscape shaped by the same geological forces that drove the regional geology of ancient Anatolia. The people who built at Göbekli Tepe and the people who first carved beneath Cappadocia were not the same culture in any direct or documented sense, but they were, in geological and temporal terms, neighbours. They lived in the same epoch, on the same landscape, in the aftermath of the same catastrophic disruptions that marked the end of the last ice age. One group built upward, toward the sky, orienting their monuments to the stars. The other carved downward, toward the core of the earth, engineering their survival into the bedrock. Both responses, in their different directions, speak to the same fundamental reality: that the surface of the world, at some point in the not very distant past of these people, was not safe. That safety required either reaching above it or descending below it. That the choice to build something permanent, above ground or below, was a response to an understanding that the world could, and had, become catastrophically hostile. That understanding did not exist in a vacuum. It was transmitted, in the only format available to people who had not yet developed writing. In the format that human beings have always used to carry the most important things across the longest distances of time. In stories, in the oldest stories ever told. Stories that every culture on Earth, on every continent, tells in a form so structurally similar that the resemblance cannot be dismissed as coincidence. Stories about the water that came and took everything, and the few who survived to remember it. Scholars who study comparative mythology have catalogued over 500 distinct flood narratives from cultures distributed across every inhabited continent on Earth. 500. From societies that had no documented contact with one another, speaking unrelated languages, living in different ecosystems, practicing different religions, organized according to different social principles. 500 stories about a time when the water came and the world ended, and a remnant survived to begin again. That number is not a coincidence. It is a signal. And understanding what it is signaling requires sitting with the stories themselves before reaching for an explanation. The oldest written flood narrative comes from ancient Sumer, the civilization that arose in southern Mesopotamia, the land between the Tigris and Euphrates rivers in what is now Iraq, roughly 5,000 years ago. In the Sumerian king list, one of the earliest historical documents ever compiled, a sequence of rulers is recorded with reigns of extraordinary and impossible length. Then the list reaches a single line that stands apart from everything around it. The flood swept over, it says. And then, kingship descended again from heaven. A new sequence of rulers begins. Something ended. Something started over. The fuller story appears in the Epic of Gilgamesh, the greatest surviving work of literature from the ancient world, composed in its earliest form over 4,000 years ago. The hero Gilgamesh, in his search for immortality, travels to the ends of the earth to find Utnapishtim, the only mortal ever granted eternal life by the gods of Sumer. Utnapishtim tells him how he earned it. The gods had decided to destroy humanity, but one among them, the god Ea, warned Utnapishtim in secret, speaking through the wall of his reed house, so that the warning could not be said to have been given directly. "Tear down your house," Ea told him. "Build a boat. Take aboard the seed of all living things." Utnapishtim obeyed. He built the boat, sealed it with pitch, loaded it with his family and with craftsmen and with pairs of every creature he could gather. The storm came. It raged for 6 days and 7 nights. The waters rose until the gods themselves were terrified by what they had unleashed. When the storm finally broke, the boat came to rest on a mountain. Utnapishtim sent out a dove. It returned. He sent out a swallow. It returned. He sent out a raven. It found dry land and did not come back. The world was beginning again. You have heard this story before. You know its structure. The divine warning, the righteous survivor, the vessel, the animals preserved, the mountain landing, the birds sent to search for dry land. You know it because it appears in the book of Genesis as the story of Noah, and the Genesis account, compiled roughly 3,000 years ago, was almost certainly shaped by the older Mesopotamian tradition that preceded it by more than 1,000 years. The earlier Atrahasis epic, dating to perhaps the 18th century before the Common Era, tells a version with additional detail. The Eridu Genesis, one of the earliest Sumerian texts, tells another. These stories were circulating in the ancient Near East for millennia before they entered the Hebrew Bible. They were not invented by one tradition and borrowed by another. They were part of the shared cultural inheritance of a region that had, at some point in its collective memory, experienced something so enormous that it could not be forgotten. But the Mesopotamian versions are not alone in the world. They are not even the oldest. In Hindu tradition, the god Vishnu appears to the sage Manu in the form of a small fish, warning him that a great flood is coming and instructing him to build a boat and load it with the seeds of every living thing. Manu obeys. The fish grows larger as the flood rises, first filling a jar, then a lake, then the ocean itself, and eventually tows the boat through the rising waters to safety on the highest mountain peak. When the flood recedes, Manu performs a sacrifice, and from the offering, a woman is born. Together they repopulate the earth. The structural parallels to the Mesopotamian tradition are exact: divine warning, chosen survivor, vessel, preservation of life, mountain landing, renewal. In Greek mythology, Zeus decides to cleanse the earth of a corrupt humanity with a flood. Deucalion, the son of Prometheus and a man of exceptional virtue, is warned by his father and builds a chest, some versions say a great boat, in which he and his wife Pyrrha survive the rising waters. When the flood subsides, the chest comes to rest on the peak of Mount Parnassus. Deucalion and Pyrrha descend, sacrifice to the gods, and are told by an oracle to throw the bones of their mother behind them. They interpret this as the stones of the earth, throw them over their shoulders, and from those stones, new human beings are born. The world begins again. In Chinese tradition, the Great Flood is not sent by the gods, but arrives as a natural catastrophe of staggering scope. The sage Gun attempts to control it by building dams, but fails. His son Yu succeeds by a different approach, not containing the water, but diverting it, dredging channels to guide the flood away from inhabited land. Yu's labor lasts 13 years. He passes his own house 3 times during that period without stopping to enter, so complete is his dedication to the task. His success in taming the flood becomes the foundation of his authority, and he becomes the first ruler of the Xia dynasty, the first dynasty in Chinese recorded history. The flood is not incidental to Chinese civilization. It is the event from which Chinese civilization is understood to have emerged. The Norse cosmological tradition approaches the flood from a different angle, but the water is there. The world begins with the melting of primordial ice by heat rising from below, creating the giant Ymir from whose body the gods later fashion the earth. When the gods kill Ymir, so much blood flows from the wound that it drowns all of the frost giants except for one pair who survive in a boat. The world of the Norse was, in its mythological foundations, a world that had already drowned once. Now move far beyond the reach of any conceivable cultural transmission from the ancient Near East. Move to the other side of the planet. Among the Aboriginal peoples of Australia, flood stories are among the oldest continuously maintained oral traditions on Earth. These are not recent compositions. They are narratives that have been passed from generation to generation, in some cases for periods that modern research suggests may extend back 10,000 years or more, to the time when the sea levels were still rising after the end of the last ice age, and the coastlines of Australia were retreating as the ocean claimed the land. Patrick Nunn of the University of the Sunshine Coast and Nicholas Reed of the University of New England published research in the Australian Geographer examining specific Aboriginal stories that describe the inundation of particular coastal features, bays, headlands, islands, in terms precise enough to match against the known geological history of sea level rise along the Australian coast. What they found was that some of these stories appear to describe real events, specific geographical transformations that occurred at specific times, events that can be dated using the physical record of post-glacial sea level change, events that happened between 7,000 and 10,000 years ago. 10,000 years of accurate geographical memory, carried in oral tradition across 300 generations, with no writing system, no maps, no external records of any kind. Think carefully about what that means. These stories are not mythology in the sense of invented narrative. They are, in the most direct sense, available to people without writing, history. They are the memory of real events, encoded in a narrative form that made them memorable enough to survive intact across a span of time that dwarfs the entire written record of Western civilization. In the Americas, the flood is equally universal. The Hopi people of the American Southwest tell of a world that was destroyed by water because its inhabitants had abandoned right relationship with each other and with the living world. A remnant was preserved, carried through the catastrophe by those who had maintained their integrity, and the world began again. The Aztec cosmology describes a sequence of world ages, each ending in catastrophe. The fourth age, the age that immediately preceded the current world, ended in a great flood that drowned everything. The survivors of that flood became the fish. The Maya Popol Vuh, one of the great literary works of Mesoamerica, describes the destruction of an earlier creation by flood. Figures made of wood, who had no memory and no reverence, were washed away by rain, and the earth was darkened. The creation that followed, the creation of humans made from maize, was built on the ruins of that earlier failed world. Across the Andes, indigenous traditions from the high mountains to the river systems of the Amazon describe floods that transformed the landscape and reorganized the human relationship to the world. On islands in the Pacific, separated from the nearest continent by thousands of miles of open ocean, flood stories persist in forms that match the structural template of narratives from cultures those island peoples had never contacted. The conventional explanation for this universality is cultural convergence. Human beings, wherever they live near water. Water floods. Flooding is a universal human experience, and extreme flooding, the kind that destroys communities and forces displacement, leaves psychological marks that find their way into the stories a culture tells about the past. The flood myth, in this reading, is not evidence of a single historical event. It is a natural product of the human condition. The story that every culture tells, because every culture has experienced water as both sustainer and destroyer. This explanation is not wrong. It is a legitimate account of how mythological traditions develop and why certain narrative structures appear repeatedly across cultures. Floods are universal. The trauma of flood is universal. The story of flood is therefore, to some degree, inevitable. But the convergence explanation struggles with the specificity of the structural parallels. It is one thing to say that every culture has a flood story. It is another to say that so many of those stories share the same sequence of events. A warning given to a specific individual, a vessel built for preservation, animals or seeds carried through the flood, a period of isolation on the water, a landing on high ground, birds sent to find dry land, a sacrifice of gratitude, a new world beginning. These are not generic features of a flood narrative. They are specific plot elements, and their recurrence across traditions that demonstrably had no contact with one another requires an explanation that cultural convergence alone does not easily provide. There is a physical reality that sits beneath all of these stories, and that the convergence explanation tends to underweight. Between roughly 15,000 and 7,000 years before the present, global sea levels rose by approximately 120 meters, nearly 400 feet, as the ice sheets of the last glacial maximum melted and returned their water to the oceans. That rise was not uniform. It was punctuated by episodes of rapid flooding, meltwater pulses, sudden releases of enormous volumes of water from collapsing ice sheets or from glacial lakes that had been dammed by ice and suddenly broke free. These pulses could raise sea levels by several meters within decades. For coastal populations living on land that had been stable for thousands of years, a meltwater pulse combined with a storm surge would not be experienced as a gradual change in the shoreline. It would be experienced as the ocean arriving without warning, advancing faster than people could run from it, swallowing fields and settlements and everything that had been built near the water. Every coast on every continent underwent this process, not once, but in episodes. The sea advancing, stabilizing, advancing again, across 8,000 years. Every coastal community that existed during this period witnessed their world being drowned by increments. And the communities that survived, that moved inland and kept moving as the water kept coming, carried the memory of what they had seen. The flood stories may not be about a single event. They may be the accumulated memory of a process. 8,000 years of coastal communities watching the ocean take their world, encoded in the only format available to people who had no other way to preserve what they knew. And if that is true, if the flood myths of Sumer and India and Greece and China and the Americas and Aboriginal Australia are the memory traces of the post-glacial sea level rise, then they are something more than mythology. They are the oldest archive of witnessed geological change in human history, a distributed multicultural record of real events preserved in narrative form across timescales that dwarf anything writing has managed to conserve. What they cannot tell us, what no story, however ancient, can tell us directly, is what existed on the land that the water took, what was built on those coastlines, what knowledge those communities had accumulated, what was lost when the sea came in and did not go back out. For that, we need a different kind of evidence. The kind that does not come from stories or stones or sediment layers, but from something far more intimate, from the bodies of the people themselves, from the molecules they left behind in their bones, and what those molecules, read carefully across thousands of years, reveal about who they were, where they came from, and what happened to them at the hinge point between the world that drowned and the world that came after. Every human being alive today carries, inside every cell of their body, a molecular archive of their ancestry. The genome, the complete sequence of genetic instructions that makes you what you are, is not just a blueprint for building a person. It is a historical document, a record of every population your ancestors were part of, every migration they undertook, every catastrophic reduction in numbers they survived, and every mixing event that occurred when previously separated groups came back into contact. Read carefully enough, with the right tools, it tells a story that no text has preserved and no archaeology has yet uncovered. Over the last 2 decades, the development of ancient deoxyribonucleic acid analysis, the ability to extract, sequence, and interpret genetic material from the bones and teeth of people who died thousands of years ago, has transformed what we can know about the deep human past. Researchers can now sequence the genomes of individuals who lived during the Ice Age, compare them to the genomes of people who came before and after, and reconstruct the population history of the species with a precision that was unimaginable a generation ago. What that research has revealed about the period spanning the Younger Dryas and its immediate aftermath is unexpected, and some of what it shows is difficult to reconcile with the conventional narrative of slow, gradual human development from simple to complex. Johannes Krause and his colleagues at the Max Planck Institute for Evolutionary Anthropology in Leipzig have been among the central figures in building the ancient deoxyribonucleic acid record for Eurasia across the Pleistocene and Holocene, the period spanning the Ice Age and its aftermath. The Institute has sequenced hundreds of ancient genomes from skeletal remains across a vast geographical range, building a picture of human population dynamics across tens of thousands of years. What emerges from that picture is not a smooth, continuous story of gradual expansion and mixing. It is a story punctuated by discontinuities, by moments where the genetic record changes abruptly, where populations that had been stable for millennia suddenly disappear from the record and are replaced by groups with different ancestry profiles, where the molecular signature of a catastrophic reduction in population size, what geneticists call a bottleneck, appears in the data. These bottlenecks are not subtle. A population that passes through a genetic bottleneck, a period of severe reduction in numbers caused by famine, disease, warfare, or environmental catastrophe, carries the signature of that reduction in its descendants for many generations afterward. The diversity of the genome narrows. Certain genetic variants that were common before the bottleneck disappear entirely because the individuals who carried them did not survive. The population that emerges from the bottleneck is genetically impoverished relative to what came before, a subset of the original, carrying only the variants that happen to be present in the survivors. Multiple human populations show bottleneck signatures in the period corresponding to or immediately following the Younger Dryas. The signal is not universal, and its interpretation is subject to ongoing debate among population geneticists, who disagree about the magnitude of the reductions and their precise timing. But the general pattern of demographic stress, population reduction, and subsequent recovery and expansion across the period spanning 13,000 to 9,000 years before the present is visible in the genomic record across multiple continents and multiple lineages. This is consistent with a period of severe environmental disruption. It does not prove the Younger Dryas impact hypothesis. It is consistent with the freshwater pulse and climate reversal hypotheses as well. But it places the genomic evidence in the same conversation as the geological and archaeological evidence, pointing at the same window of time as a period of profound disruption to human populations worldwide. Now look at what the genetics reveal about the specific people who built Göbekli Tepe. The builders were pre-pottery Neolithic Anatolians, a genetically distinct population that inhabited the region of modern Turkey during the period spanning roughly 10,000 to 7,000 before the Common Era. Ancient deoxyribonucleic acid extracted from skeletal remains found at sites contemporaneous with Göbekli Tepe and its cultural successors has allowed researchers to characterize this population with considerable precision. They were not the same people as the hunter-gatherers of Western Europe, or the populations of the Levant, or the peoples of the Zagros Mountains to the east. They were genetically distinct, a separate lineage with a specific ancestry profile that reflects their own deep history in Anatolia. What happened to them subsequently is one of the most dramatic demographic events in the post-glacial period. Around 9,000 to 8,000 years before the present, the same general period when Göbekli Tepe was deliberately buried, the pre-pottery Neolithic Anatolians began expanding out of their homeland. Not as raiders or conquerors, but as farmers, carrying with them the domesticated crops and animals that had been developing in their region for centuries. They moved westward into Europe, southward into the Levant, and their genetics, their specific ancestral signature, became the dominant component of the Neolithic farming populations that spread across the continent over the following 3,000 years. Today, a substantial fraction of the ancestry of every European traces back to these people. The descendants of the builders of the world's oldest temple are among your own ancestors, if you have any European heritage at all. They did not disappear. They dispersed, carrying what they knew. But where did the pre-pottery Neolithic Anatolians themselves come from? Who were their ancestors? And what does the genetic record say about the deep history of the population that produced Göbekli Tepe? This is where the picture becomes less clear and more interesting. The pre-pottery Neolithic Anatolians appear in the genetic record as a relatively homogeneous population, suggesting that by the time we can sequence them, they had already been through a period of isolation and reduced genetic diversity. Their ancestry pulls from sources that were widespread during the Ice Age, but had become mixed and stabilized into a distinct profile. The basal Eurasian ancestry component, a deep genetic lineage that contributed to populations across the ancient Near East, and that appears to have diverged from other Eurasian lineages very early in the dispersal of modern humans out of Africa, is present in their genomes at high levels. This component is ancient, It points to a deep history in a region whose Ice Age geography was substantially different from the present. What the genetics cannot tell us directly is the nature of the society these people were part of before the Younger Dryas. The skeletal remains available for sequencing date from after the catastrophe, not before it. The people we can genetically characterize are the survivors and their immediate descendants. The population that rebuilt, that began cultivating crops, that constructed Göbekli Tepe in the immediate aftermath of the Cold Period. Who they were before the disruption, what social structures they maintained, what level of organization they had achieved. These questions cannot be answered from the molecules alone. But the molecules do tell us something important about scale. Population genetics can estimate the effective size of a past population, the number of individuals who are actually contributing to reproduction at any given time, from the diversity patterns in the genome. For the pre-pottery Neolithic Anatolians and related Ice Age populations in the region, those estimates suggest groups of moderate size, not tiny isolated bands, but populations numbering in the thousands to tens of thousands across a substantial geographical range, connected by enough gene flow to maintain genetic coherence across that range. Gene flow between populations means contact. Contact means movement. Movement across a substantial geographical range, maintained consistently enough to produce measurable genetic mixing, means a level of social connectivity that goes beyond isolated bands wandering in search of food. It means networks, trade routes, or their pre-agricultural equivalents. Seasonal gatherings at specific locations, the kind of repeated, structured interaction between groups that is the social foundation of any larger organizational capacity. Göbekli Tepe required that foundation. The geometric planning of its enclosures, the coordination of labor from across the region, the sustained construction program that lasted thousands of years, none of that is possible for a genuinely isolated population. The genetic evidence of regional connectivity during the pre-pottery Neolithic is, in this sense, supporting evidence for the archaeological reality of what was built. The people who built Göbekli Tepe were not alone. They were connected, and whatever they knew, whatever organizational and technical capacity they possessed, was the product of a social network operating across a substantial region. What that network looked like before the Younger Dryas, whether it was more extensive, more organized, more sophisticated than it was in the immediate aftermath of the disruption, is a question the genetics alone cannot answer. Bottlenecks reduce diversity. Populations that pass through catastrophic reductions in size lose not just genetic variance, but cultural complexity. Knowledge that is not encoded in surviving individuals is lost. Skills that are not taught before the catastrophe are not available afterward. The survivors rebuild from what they retained, which may be a fraction of what existed before. This is the most sobering implication of the genetic bottleneck evidence. If the populations of the ancient Near East passed through a severe reduction around the Younger Dryas boundary, if the catastrophic events of 12,800 years ago compressed and reduced the human populations of the region to a fraction of their previous size, then what we see in the genetic and archaeological record of the early Neolithic may not be the beginning of something. It may be the recovery from the near end of something. Göbekli Tepe, on this reading, is not the first flowering of human organizational complexity. It is the reassertion of it, built by survivors who retained enough knowledge to build something extraordinary, but who were beginning again from a position of reduced numbers, reduced resources, and a landscape that the catastrophe had reorganized from the ground up. This interpretation is not proven. It is a reading of fragmentary evidence through a particular lens, and the lens can be questioned. The conventional reading, that Göbekli Tepe represents the emergence of new organizational capacity, rather than the recovery of old capacity, cannot be dismissed. The evidence does not definitively choose between them. But the genetic bottleneck is real. The demographic disruption at the Younger Dryas boundary is real. The extraordinary sophistication of what was built immediately afterward is real. And the gap between what the survivors apparently knew and what the conventional model suggests they should have known, that gap has not yet been satisfactorily closed. What we are looking at, across the genetics and the archaeology and the geology, is not a mystery with a single hidden answer waiting to be found. It is a question with a frontier, a boundary between what the evidence currently supports and what lies beyond it, in the unexplored territory that the tools of the last century were not designed to enter. Those tools are changing, the frontier is moving, and the territory that is opening up, beneath the ocean, in the genomes of ancient bones, in the sediment layers of unexplored sites, may contain answers that none of the frameworks currently competing to explain the deep human past have fully anticipated. Which brings us back to the question Frank and Schmidt put into print in 2018, not as a conclusion, as a starting point, a formal acknowledgement that the boundary of our knowledge is not where we assumed it was, and that the most honest thing science can do with a question it cannot answer is not to pretend the question has been settled, but to describe, with as much precision as possible, exactly where our certainty ends. That description is where we are going next. There is a discipline within the study of fossilization called taphonomy. It is the science of what happens to organisms after they die, how they decay, how they are buried, how they are preserved or destroyed, and what the resulting fossil record actually represents about the living populations that produced it. Taphonomists spend their careers thinking about absence, about what did not survive, about the gap between what once existed and what the rock has chosen to keep. One of the foundational findings of taphonomy is that fossilization is extraordinarily rare. The conditions required for an organism to leave a detectable trace in the geological record, rapid burial in fine-grained sediment, the right chemical environment, the absence of scavengers and bacteria that would otherwise consume the remains entirely, protection from the erosion and tectonic processes that would subsequently destroy the deposit, are met for only a vanishingly small fraction of any organism that ever lived. Estimates vary, but the consensus among paleontologists is that the total number of individual dinosaur fossils ever found from a group of animals that dominated the planet for 165 million years on every continent, in enormous numbers, could fit inside a single large museum. 165 million years, every continent, enormous numbers, one museum. Now consider what this means for a civilization. A civilization occupies a tiny fraction of the Earth's surface, less than 1% of the land area, clustered along coastlines and river valleys. It exists for a few thousand years at most in geological terms, and it leaves behind not bones, which are at least biological material with some chance of preservation, but structures made of stone, metal, glass, and composite materials that weather, corrode, dissolve, and fragment at rates that make fossilization look leisurely by comparison. The argument that the absence of evidence for a previous civilization constitutes evidence of its absence rests on an assumption that is rarely examined, that we would find it if it existed, that our archaeological and geological tools, applied to the surviving fraction of the Earth's surface record, would reliably detect the traces of something that existed millions of years ago and has been subjected to the full force of geological destruction ever since. That assumption is not supported by what we know about how the geological record works. William Ruderman, a paleoclimatologist at the University of Wisconsin-Madison, spent years developing a hypothesis that has become known as the early Anthropocene. His argument, first published in 2003, is that human beings began altering the composition of the Earth's atmosphere not with the Industrial Revolution of the 18th century, but thousands of years earlier, through large-scale forest clearance for agriculture and through the methane emissions of irrigated rice paddies. The carbon dioxide and methane signals of these activities, Ruderman argued, are detectable in the ice core record going back 8,000 years. The early Anthropocene hypothesis remains contested. Other researchers have proposed natural explanations for the same signals in the ice core record, and the debate about the relative contributions of early human land use and natural variability has not reached resolution. But the hypothesis demonstrates something important, regardless of whether it is ultimately correct, that substantial human modification of the global carbon cycle can produce a signal in the geological archive that is ambiguous, contestable, and easily attributed to natural processes by researchers who are not specifically looking for a human cause. If 8,000 years of agriculture and forest clearance, involving millions of people across entire continents, can produce a signal that is this difficult to distinguish from natural variability, what does that say about the detectability of a civilization that existed for a few thousand years, millions of years ago, in a geological record that has been through multiple cycles of subduction, erosion, and metamorphism since? Here is the epistemological position stated as precisely as it can be. We have examined a small fraction of the Earth's surviving surface record. That record represents a tiny, unrepresentative sample of what once existed, filtered through billions of years of systematic destruction. Within that sample, we have found no unambiguous evidence of a previous industrial civilization. On the basis of this finding, we have concluded that no such civilization existed. The logical problem is obvious once you see it. Absence of evidence in a heavily filtered, largely destroyed, incompletely examined record is not the same as evidence of absence. The confidence with which the conclusion has been stated is not proportionate to the quality of the evidence on which it rests. This is not a call to abandon skepticism or to accept claims that lack evidence. It is a call to be precise about what we actually know. And what we actually know is this: we have not found evidence of a previous civilization. In a record this incomplete, this selectively preserved, this thoroughly processed by geological time, that finding carries far less weight than it would in a more complete archive. Frank and Schmidt were explicit about this. Their paper was not an argument for the existence of a previous civilization. It was a formal analysis of the limits of our ability to detect one. The distinction matters enormously. One is a positive claim requiring positive evidence. The other is an epistemological statement about the boundaries of knowledge. And epistemological honesty, knowing what you do not know, being precise about the limits of your certainty, is not a weakness in science. It is a prerequisite for doing it well. There is a pattern worth naming directly. The history of science is populated with confident absences that turned out to be wrong. For most of the 19th century, the confident absence was the absence of evidence for continental drift. The shapes of the continents, the distribution of fossils, the alignment of geological formations across oceans were all there, but the mechanism was not understood, and the idea was dismissed. The absence of a mechanism was taken as evidence of absence of the phenomenon. It was not. For decades, the confident absence was the absence of evidence for an impact cause for the end Cretaceous extinction, until the iridium layer was found in rock around the world, and the Chicxulub crater was identified beneath the Gulf of Mexico. The absence of a crater had been taken as evidence that no impact occurred. The crater had simply not been found yet. Each of these reversals followed the same pattern. The evidence had been there, or was there to be gathered. The tools or the perspective needed to see it had not yet been developed. The confident absence was a statement about the limits of current knowledge, dressed up as a statement about reality. The submerged continental shelves of the Ice Age world are the most important unexamined territory in this discussion. And they are, in the most literal sense, a frontier, a boundary between what has been investigated and what has not. Consider the specific geography. The Persian Gulf Basin was entirely dry during the last glacial maximum. It is a shallow sea, most of it less than 30 meters deep, sitting above what was, 20,000 years ago, a river valley running between the Arabian Peninsula and the Iranian highlands, draining into the Indian Ocean through a narrow strait near the modern Strait of Hormuz. The climate of that valley, sheltered by the surrounding highlands and watered by rivers draining from both sides, would have been among the most hospitable environments in the Ice Age world. Warm, protected, well-watered, rich in resources. And it is now underwater, beneath a sea that formed when the post-glacial rise reached its basin and filled it roughly 8,000 years ago. The Sunda Shelf, the vast continental platform beneath the shallow seas of Southeast Asia, connecting the modern mainland to Borneo, Java, Sumatra, and the Philippines, was exposed as a continuous landmass for most of the last 100,000 years. It was dry land, larger than modern India, with river systems, forests, and coastlines stretching thousands of miles. Modern humans arrived in Australia at least 65,000 years ago, crossing water that at the time was considerably less daunting than it is today. The people who made that crossing were living on Sunda, on land that is now ocean floor, for tens of thousands of years before the sea reclaimed it. We have barely looked at that seafloor. What is preserved there, if anything is preserved, remains unknown. The Sahel Shelf along the northwestern coast of Australia, the continental margins of India, the North Sea basin of Doggerland, the coastal platforms of the Americas that extended the shoreline of North and South America hundreds of miles into what is now ocean. Each of these represents terrain that was inhabited, that was geographically significant, and that has been underwater for between 7,000 and 12,000 years. Marine sediment can be a remarkable preservative. In cold, deep, oxygen-poor water, organic material survives that would decompose in days on land. Wood, bone, charcoal, pollen, the chemical signatures of fire and human activity. All of these can survive in deep marine sediment in conditions that render them retrievable by the right instruments. The technology to survey these landscapes systematically now exists. Multi-beam sonar can map the topography of the seafloor with a resolution sufficient to identify river channels, lake beds, coastal features, and structural anomalies. Sub-bottom profiling can penetrate the sediment and reveal what is buried beneath it. Remotely operated vehicles can be sent to investigate specific features identified from the surface. Sediment cores can be extracted and analyzed for chemical signatures and biological remains. These tools are not experimental. They are operational. They are used routinely in marine geology and in the offshore energy industry, which has mapped large portions of the world's continental shelves in the course of searching for oil and gas. Some of that mapping data is directly relevant to Ice Age landscape reconstruction, and researchers have begun to use it. The Doggerland surveys off the British coast have already demonstrated what is possible. A submerged landscape revealed in detail sufficient to identify ancient river systems, reconstruct the topography of an Ice Age environment, and locate evidence of human habitation in sediment cores from what is now the bottom of the North Sea. That is one shelf, one relatively small section of the total submerged Ice Age world. And it has already yielded evidence of people living on land that is now ocean floor, at depths consistent with the post-glacial sea level rise. The surveys of the Sunda Shelf, the Persian Gulf Basin, the Sahel Shelf, the Indian continental margin, these have not been done, not systematically, not with the explicit goal of reconstructing Ice Age landscapes and searching for evidence of human occupation. The resources, the institutional priority, the organized scientific program needed to conduct that survey do not yet exist at the scale the question requires. The absence of findings from the submerged shelves is therefore not a finding. It is a gap, an uninvestigated space in the evidence record, and uninvestigated spaces do not support conclusions in either direction. What is sitting in those sediments, whether it is the ruins of structures, the chemical signatures of human activity, the preserved remains of settlements on coastlines that have been underwater for 10,000 years, or simply the undisturbed geological record of a landscape that was inhabited and then drowned? We will not know until we look. The question is not whether something was there. The question is whether we are willing to ask it seriously enough to go and find out. And the answer to that question is not a matter of science. It is a matter of priority, of what we decide is worth knowing. The decision has not yet been made. The investigation has not yet begun. The most important unexamined archaeological frontier on Earth is sitting at the bottom of the ocean, under sediment and salt water and 12,000 years of silence, waiting for the first systematic survey that will tell us, one way or another, what the Ice Age world looked like when the water came in and did not stop. Whatever is down there, or is not down there, the answer will change this story. In one direction or another, it will change it fundamentally. and we are closer to having the tools to find it than at any previous moment in the history of the species asking the question. That is not a small thing. That is the beginning of the end of not knowing. We began with a layer of rock that should not exist. A thin chemical anomaly, running through sediment cores, pulled from the floors of oceans and the depths of Arctic ice, marking a moment 56 million years ago when something happened to this planet that our best science has still not fully explained. A moment that looks, in its chemistry and its consequences, disturbingly like what we are doing to the Earth right now. That resemblance is not the point of this story, but it is the warning encoded inside it. Let us take stock of where we have been. We have followed the Silurian hypothesis from the desk of a NASA climate scientist to the deepest implications of the geological record. We have examined the Paleocene-Eocene thermal maximum, not as a settled historical curiosity, but as an active scientific debate whose trigger remains contested, whose carbon isotope signature carries an uncomfortable ambiguity, and whose global consequences serve as the closest ancient analogue we have for the trajectory our own civilization is currently on. We have traced the evidence for a cosmic catastrophe at the Younger Dryas boundary, the impact proxies in the sediment, the craters under the ice and in the American South, the destruction layer at one of the world's oldest agricultural sites, the simultaneous collapse of an entire megafaunal community, and the culture that hunted it. We have stood inside the enclosures of Göbekli Tepe and tried to absorb what it means that hunter-gatherers built this 11,500 years ago with flint tools to a geometric plan in the immediate aftermath of the worst climate disruption of the last 20,000 years. We have examined the erosion on the walls of the Sphinx enclosure and followed the processional astronomy to its conclusion. We have descended 85 meters beneath the surface of Cappadocia and asked why anyone would go that deep unless the surface itself had become a place where survival was impossible. We have listened to 500 flood stories from 500 cultures and noticed that they all say the same thing. We have read the genomic bottlenecks in ancient bone and understood what severe population reduction means for the knowledge that does not survive it. And we have stood at the edge of the submerged continental shelves and acknowledged, honestly, that the most likely location for any pre-glacial coastal civilization is sitting under water we have not yet surveyed. None of this proves that something was here before us. The conventional explanations for each of these phenomena are real, are supported by evidence, and in most cases are probably correct. The Silurian hypothesis is a thought experiment, not a discovery. Göbekli Tepe is extraordinary, but extraordinary does not require a previous civilization to explain it. Only a more generous assessment of what pre-agricultural human beings were capable of. The Sphinx erosion is disputed geology, not settled science. The flood myths are universal, but universality can arise from convergent cultural experience as well as from shared historical memory. The genetic bottlenecks are real, but catastrophic population reductions have many causes. The honest position, the scientifically defensible position, is that we do not know. We do not know whether anything came before us on this planet in the sense that would qualify as civilization. We do not know because the geological record is an incomplete archive of a world that has been systematically destroying its own history for 4.5 billion years. We do not know because the most likely locations for any evidence are underwater and unexamined. We do not know because our tools were not designed to look for this. And the question has only recently been asked in a form precise enough to be investigated seriously. Not knowing is not a comfortable position. Human beings are not built for it. We want resolution. We want the story to end with an answer. The absence of a conclusion feels like a failure, as if the evidence should have delivered a verdict by now, and the fact that it has not means something was done wrong. But not knowing, stated precisely and honestly, is not the same as having found nothing. It is a description of the current boundary of knowledge. And the boundary is moving. Here is what has changed in the last decade alone. The Hiawatha crater did not exist in the scientific literature before 2018. It is now a documented 31-kilometer impact structure under the Greenland ice sheet. The Abu Huraira glass was not analyzed in the context of cosmic impact until 2020. The ancient deoxyribonucleic acid record for the pre-pottery Neolithic Anatolians barely existed 15 years ago. Now it is substantial enough to characterize the genetic identity, the population size, and the dispersal history of the people who built Göbekli Tepe with considerable precision. The submerged landscape archaeology of Doggerland has moved from theoretical framework to active research program, producing real findings from real sediment cores on the North Sea floor. The pace of discovery is accelerating, not because the questions are getting easier, but because the tools are getting better. Airborne radar that can see through kilometers of ice. Ancient deoxyribonucleic acid analysis that can reconstruct population histories from fragments of bone too small to see without magnification. Multibeam sonar that can map the topography of a submerged landscape in detail, sufficient to identify a river channel from 12,000 years ago. The instruments that did not exist a generation ago are now producing findings that are reshaping the story in real time. And underneath all of it, underneath the geology and the archaeology and the genetics and the oceanography, the question that Frank and Schmidt formalized in 2018 continues to expand its implications. Not just the question of whether something came before us, but the question of what we are leaving behind. Because here is the thing that the Silurian hypothesis, taken seriously, forces you to confront. It is not primarily a question about the past. It is a question about the present, about what we are doing to this planet, and what the geological record of that activity will look like 50 million years from now to whatever intelligence finds it. We are currently producing 300 million tons of plastic annually. The radioactive isotopes from over 2,000 nuclear weapons tests are distributed globally in soil, sediment, and ice. A signature so distinctive that it has been proposed as the formal marker of the Anthropocene in the geological record. We have altered the carbon isotope ratio of the entire atmosphere. We are driving species to extinction at a rate that matches the great mass extinctions of the deep past. The events that left their signatures as boundaries in the rock, the moments when the fossil record reorganizes itself entirely above a specific line. We are, in geological terms, creating a mass extinction event in real time. We are creating our own boundary layer. We are writing ourselves into the rock. The International Commission on Stratigraphy, the body responsible for formally defining geological time, has been debating for years whether and where to place the beginning of the Anthropocene as a formal geological unit. The debate is not about whether human activity has left a detectable mark in the geological record. It has. The debate is about exactly when the mark becomes unambiguous enough to serve as a stratigraphic boundary. The answer, when it comes, will establish in the official language of geology that we are the first species to have altered the chemistry of a planet sufficiently to be readable in the rock record. The first species we know of, at least. The PETM sits in the rock 56 million years ago as a warning that carbon release at scale has consequences that operate on timescales no civilization has ever had to reckon with. The recovery from the PETM took 100 to 200,000 years. The species that were lost in its deep ocean mass extinction did not come back. The ecological communities that were reorganized by its disruption did not return to what they had been. The event resolved, eventually, because the Earth is a system with negative feedbacks, processes that gradually pull carbon back out of the atmosphere and restore chemical balance. But the resolution took longer than modern humans have existed as a species. And whatever caused the PETM, volcanic intrusion, methane hydrate collapse, orbital forcing, or some combination of all three, it did not choose to do it. It was not a decision. It was a mechanism. We are a mechanism that can make decisions. That is the distinction that separates us from every natural process that has ever altered this planet's chemistry. Not the alteration itself. Carbon release events have happened before, and the rock records every one of them. What separates us is the capacity to understand what we are doing while we are doing it, to read the geological record of past carbon events and recognize our own reflection in them. To look at the PETM and understand, not as mythology or metaphor, but as straightforward physical consequence, what the trajectory we are on leads to. Frank and Schmidt were not writing a paper about a lost civilization. They were writing a paper about us, about the mark we are leaving, about what the record we are creating will look like when the tools capable of reading it are finally brought to bear on the question, whether those tools are wielded by human beings 1,000 years from now, or by something else, something that emerged from the planet's next attempt at intelligence, peering at a strange thin layer in the rock and wondering what made it. The Göbekli Tepe builders carved their memorial into limestone on a hilltop in Turkey because they understood that stone outlasts memory. The Aboriginal Australians encoded the geography of a drowned coastline into stories because they understood that narrative outlasts the landscape. The builders of Derinkuyu went 85 meters underground because they understood that sometimes the only way to preserve something is to take it out of reach of what is coming. Each of these was an act of deliberate preservation in the face of known or anticipated loss. We know what is coming, not with the certainty of a comet on a confirmed trajectory, but with the probabilistic confidence of physics and chemistry applied to a carbon cycle that has been pushed outside its recent historical range. We know because the rock has told us. The PETM is there, in the sediment record, a permanent and perfectly legible account of what happens to a planet when its carbon balance is disrupted at this scale and this speed. The question is not whether we will leave a mark. We already have. The question is, what kind of mark it will be. The thin, ambiguous chemical whisper of a civilization that burned through its resources and collapsed before it understood what it was doing, or something more legible. Something that a future intelligence, running its analysis on a core sample from what was once the floor of the Atlantic, might look at and say, they knew. They read the record. They understood what they were inside of. The rock is patient. It has been keeping accounts for 4.5 billion years, and it will continue long after every structure we have ever built has been dissolved back into sediment. What we put into the account is still being written. That thin layer in the rock, the one we began with, the one that runs through cores from 6 continents, the one that marks a moment 56 million years ago that our science has not yet fully explained, is a message, not from a civilization, from the planet itself. A demonstration of what carbon release does, written in the language of chemistry and preserved in stone, addressed to whoever developed the tools to read it. We have the tools. We can read it. Whether we do anything with what it says is the only question that has ever really mattered.